Good morning, everyone. So I'm very glad to be here and looking forward to today moving on to what we know about Earth's magnetic field today, the present geomagnetic field. So we'll talk about the observations we have of Earth's magnetic field from observatories and from satellites, and then we'll talk about how we build global reference models from that data. So as an introduction to myself, so yes, as Barbara mentioned, I'm working at the Technical University of Denmark in Copenhagen. I'm a professor of geomagnetism there. My background is that I'm originally Irish, but I have worked in England and Switzerland studying physics and geophysics for now some decades. But today I'm actually curious, first of all, about what your backgrounds are. So I'm not sure exactly what fields you're all from and what level of understanding you already have on these topics. So I was wondering, how many of you are working in sort of paleomagnetism type topics? So there's a few paleomagnetists. What about space weather, space physics topics? Yes, okay, so many in space weather, space physics topics. Is there anyone who's working with ground observatory data? Yeah, okay, so some there. And what about satellite observations? Yeah. And finally, how many of you know what spherical harmonics are? We're going to come back to that this afternoon, but just so I know. So I'm going to teach today assuming that we don't know too much to get you the basic information about the observations and the tools you need to hopefully reach the research level and understand some of the talks that are coming next week at the conference. And as Barbara mentioned, we'll have some practical that Ashley will be helping out with on these different topics. So we'll come back to that later on. So the rough outline for today, I'm going to start off with an introduction to the present magnetic field and talk about first ground observatory, geomagnetic observatories. Then we'll take a break and then we'll come back to a practical on the observatory data. Then I'll talk about satellites before lunch. Then after lunch, we'll go on to more of the theoretical modeling part, talk about this IGRF, the International Geomagnetic Reference Field, and then I'll finish off at the end of the day with some more state-of-the-art models focused on different sources of the field. So what I hope by the end of today is that you'll have some tools that will help you then to explore any of these topics that you're interested in further. And I should say, please interrupt as we go along and ask questions. If I'm going too fast or skipping something, I'd really be happy if you stopped me and said, okay, what do you mean there? So I look forward to the discussions here. Now, I won't have a chance to go through everything in just one day, so if you're interested in going further with this, there's some basic references here. So there's recently been a book published by William Lowry on the Earth's magnetic field, which I think is a very nice introduction, not too technically detailed, but it discusses all the different sources and many of the things that I'll mention today at a fairly easy introduction level. There's a book by Blakely which discusses a lot more of the theory of potential fields and spherical harmonic modeling. And the kind of classic reference is four volumes on geomagnetism by Jacobs. And in particular, volume 1 of that talks about many of the topics we'll discuss today. There are also more up-to-date review articles, in particular in the Treatise of Geophysics. There's an article by Gauthier-Hulot and colleagues on the present field and on secular variation by Andy Jackson. And there's also a very nice encyclopedia of geomagnetism and paleomagnetism, where if you want a short article on some of these topics, I can recommend looking in there. So these resources, I hope, will also be useful to you if you're coming back to this. And the slides, I should say, are uploaded onto the shared drive, so you can hopefully see those and make notes as you're going along. Right, so now let's have a very quick introduction to the present geomagnetic field. So I think we should start here with how we all experience the magnetic field. So The most basic experience we have as humans of the magnetic field is if you take a magnetized needle and you balance it, for example, in a horizontal plane, and you're away from man-made disturbances, you know that it will tend to point in the direction of the local magnetic field. And that's often approximately towards north, but not exactly. This is a very first-order observation. We've all seen that with a compass. Maybe what we haven't seen with a compass is if you took the needle and allowed it to tilt in the vertical axis, we would see the needle would be dipping down into the earth. And this is telling us that the magnetic field is not just in the horizontal plane, it's also dipping down. And here in the northern hemisphere at the moment, it's dipping down through this room at a steep angle between 60 and 70 degrees. And in addition to these two directions of the magnetic field will also have a strength. And we're really sitting here today embedded in this magnetic field, even though we're not aware of it. And humans have long been curious about this, but today we don't use these magnetized needles usually to measure it. We've developed accurate instruments, in particular things like flux gate magnetometers, which we'll talk about in some detail, which measure the magnetic field in 3 perpendicular axes. And we also today have much smaller and also less accurate magnetometers, and many of you will have one sitting in your mobile phone, and that's helping people to find their orientation. So in there's a magnetometer measuring the local magnetic field, and if we then have a reference which tells us at this location what direction we expect the magnetic field to be in, we can take this measurement and find out what direction we're pointing. So this is how we get orientation information. So there are billions of users of the present geomagnetic field for orientation information. All you need is a magnetometer, and you need a good map, a good model of the present magnetic field. Okay. And it's also rather interesting that many animals are sensing the magnetic field. So we as humans aren't aware of that, but they're using that as part of the information that they take in and then use to find their way around. So I guess humans are a little bit different because we develop tools that then allow us to use the magnetic field. But the basic point about the magnetic field is it's a vector, right? So that means we need 3 numbers to characterize it. So that could be 3 perpendicular directions, downward, eastward, northward, or it could be 2 angles, the declination angle between the geographic north and the local magnetic direction, the inclination or dip angle, which the magnetic field is making below the horizontal, and the strength of the magnetic field. So to fully characterize the magnetic field, you always need these 3 numbers, either the 3 perpendicular directions or 2 angles and a strength. So these are the things we want to measure if we want to characterize the magnetic field that's all around us. So what's interesting, so we have this magnetic field all around us, but if I then move to another location, the direction and strength of the magnetic field changes slightly. Okay, so it's varying with spatial position. So what's shown here is 1 day of measurements taken by the SWARM satellites. So we'll talk about those more later this morning. So here the color is showing you the strength of the field, and the line is showing you the direction of the field. So you'll see at higher latitudes the field is typically stronger, and the direction is changing depending on our exact location. So the field varies with spatial location. If we then take lots of such measurements, we can turn that into a continuous model, and this is an example of a map of the radial part, so the vertically outward part of the field at the Earth's surface. So we see there are certain regions where this radial field is stronger, especially south of Australia, in Siberia and Canada, and it's less strong in the southern Atlantic region. So we need to think about characterizing what the magnetic field's properties are at all locations, somehow simultaneously, if we want to fully characterize it. So another way to look at spatial variations is to look at that in the spectral domain. So this is a power spectrum showing the amount of power of the magnetic field on the y-axis against what's called the spherical harmonic degree on the x-axis. So this is like inverse of the spatial wavelength. So degree 1 here is very large length scale, the dipole, and degree 200 is much smaller scale variations. So here we can see that most of the energy in the magnetic field is on large scales. So this is this dipole part, quadrupole part, and this drops off rather rapidly. And then at some point it becomes almost flat. And these two lines here are showing some simple theoretical models of sources either in the Earth's core, which is a red line, or at the Earth's surface, which is the blue line. So this spectrum is showing us that we have different depths of sources that are contributing to the magnetic field on different length scales. So the large length scales, we have signal from the core, and on smaller length scales, we have the signal coming from close to the Earth's surface. So there's spatial variations happening across a large range of scales. And today, the most detailed spatial map of the Earth's magnetic field we have is this World Digital Magnetic Anomaly Map. So here, this is showing all the local variations of the magnetic field. So as you move from one place to another, you might be standing over a strongly magnetized rock or piece of geology that's strongly magnetized, and there you'll measure a slightly different value for the magnetic field. So there's really spatial variations happening on lots of different length scales, reflecting processes in the Earth's core and the geology near the surface. That's how things vary with position. What's also interesting is if we just went into a quiet area here near Lisbon and measured how the magnetic field changes as a function of time, we'd see temporal variations in the magnetic field. So this is in fact a time series, a long time series from Niemenke Observatory in Germany. So this has got nearly 100 years of data going back to the 1930s. This is the eastward component of the magnetic field. And you see here there's a very long-term trend, right? So this is saying that there's a slow variation in this main part of the magnetic field. And then you can see there's what looks like here, when we're very zoomed out over 100 years, like some kind of noise, right? Looks like scatter. But if we zoom into this, so now this is 1 year of data from the observatory from 2024. And now you see, yeah, okay, there's this higher frequency variation, but you see that it's systematically changing its amplitude over the year. So it's somehow less at the start and end of the year, which is winter, and it's a bit larger in the summer time. And then there are some times when there's what looks like spikes here over a year. So we can zoom in further, and now this is 2 months of data from the 1st of April 2024. And now you see what looked like noise, scatter. You see that every day there's a variation. This is the so-called daily variation, the solar quiet variation. And this is often the same when there's not much happening from the sun, which is driving currents in the upper atmosphere. So the terminology we use studying the present field is to say when there's this daily variation and not much else happening, things are quiet, geomagnetically quiet. So there are quiet times, and then here you see on the 11th of May, there was a big spike. So this was this so-called geomagnetic storm that happened on the 11th of May, 2024. And so this is not noise, right? These things that look like spikes on the first plot, these are very good measurements, right? And what they're showing you is different processes. So There's temporal variations happening in the present magnetic field on long time scales associated with the core, on daily variations, and then occasionally some sharp variations. Yes, there was a question.
Because geomagnetic storm,
Yeah,
usually the Earth's field weakens, right?
yeah.
So should it increase or it should decline? Because we have the DST value, so
Yeah. Yeah, so this is the eastward component of the field. Normally when you're looking at DST, for example, that's the northward component mostly that you're looking at. So if I showed you the other component, it would look more like this classic storm, especially if we zoomed in to just a few days. There's this main phase where the disturbance is largest, and then it gradually decays over several days. You're right. So it depends what field component we look at. Yeah, so there's a lot going on, and we have a lot of great data to look at here. If we take then a power spectrum in time, so we looked at the power spectrum in space. This is a power spectrum in time of the geomagnetic field. So this has got frequency on the x-axis and power on the y-axis. So on the very low frequencies, you have things that the paleomagnetists are interested in. You have things like reversals, excursions, and then you have secular variation on time scales of centuries to decades. That was that long-term trend we saw in the NEMANC data. And then when you get into this range about 1 year, 6 months, then you start to see some very specific periods, these spikes here. This was the daily variations. Then if you go to even higher frequencies, eventually you'll see different things related to space physics, and eventually you'll see anthropogenic signals from power lines, navigation. So my focus today is going to be more in this range, secular variation down to about 1 year, because I'm mostly interested in the internal field. But when you measure the Earth's magnetic field, you have to deal with all this, because all this is in what you're measuring, right? That's also what makes it interesting. So what's causing these variations that we see? So the source of a magnetic field is fundamentally an electrical current. So for Earth's magnetic field, the origin of it is natural electrical currents. And the majority of this is coming from the dynamo process in the liquid outer core, where we have motions of the liquid metal that are transferring kinetic energy into electrical energy, currents that then give Earth's magnetic field. The faster variations we see mostly come from currents in the upper atmosphere, either magnetospheric currents going out from the interaction of the solar wind and the Earth's magnetic field. And we also then have currents in the ionosphere and coupling currents between the ionosphere and the magnetosphere. We also have magnetization of the crust that affects the small spatial scale variations of the magnetic field.
excuse me, Chris.
Yep.
So the magnetic field mainly come from the fluid core on the soil.
Yeah, so it's typically more than 90% is coming from the fluid outer core, depending on where you're measuring and assuming there's not a magnetic storm or something happening. So typically, say here at mid-latitudes, you have maybe 50,000 nanoteslas coming from the Earth's core, and these daily variations, they might be 20 or 30 nanoteslas, and if you had a storm, that might be somewhere between 100 and maybe even 1,000 nanoteslas. But by far the biggest source of this magnetic field is in the fluid core. Yeah. So again, when we're looking at measurements, we're measuring the superposition, the combination of the signal from all of these sources. And that also informs what scientific questions we can be interested in when studying Earth's magnetic field. So the questions we're trying to address with the magnetic field data are what's happening in the Earth's core. We just mentioned that's where most of the field is generated. So what's happening to these motions of the liquid metal there? Why is the magnetic field changing? It's an important question. We don't know all the answers to that. We're interested in what is the magnetization of the crust, the lithosphere, for example, related to different geological and tectonic processes. We're interested in What are the currents in the ionosphere? How are they changing as a function of position and time, and maybe with the sun's position? And also this very dynamic magnetospheric currents. How is the energy being transferred from the sun into these different current systems? So these are all the scientific questions that we can get at with the measurements we make of the present magnetic field. And these are the scientific things that are driving our curiosity. But there's also some practical reasons why we're interested in the present magnetic field. And so although we don't talk about it a lot, Earth's magnetic field is really a very important part of our planetary habitat. And we can see a different situation if we look at Mars. So Mars doesn't have a strong global core field. It has some magnetized rocks at the surface. And so what we can see on Mars, and there's been measurements by NASA's MAVEN mission that have shown this, that the atmosphere of Mars is being continuously stripped by the solar wind because it doesn't have this strong magnetic field. So that's an important motivation for studying this core dynamo process and how it's changing. It's a fundamental part of our natural environment. The other reason that it's of interest and that society is interested in us knowing about the Earth's magnetic field is that it provides, as I mentioned on the first slide, this orientation information. So GPS can tell you where you are, but if you want to know what direction you're pointing, you can use measurements of the magnetic field to do that. And so people are using that in their smartphones all the time. For aircraft and air traffic control, GPS can have problems. It can be jammed, or it can fail if there's large solar storms. The magnetic field is always present and can always be used, still used as a backup for many applications. Also, it can be used below the ground. If we're drilling below the ground, for example, for geothermal energy is an up-and-coming application at the moment, then you need to know which direction you're drilling, and for that you can use the magnetic field. You can't use GPS below the ground. Also for identifying mineral deposits of interest, you can use studies of these local magnetic anomalies. So there's a lot of important societal applications as well here. So that was just oh yes, a last thing is that you should all in this room feel like you're part of a long history of scientists who have been fascinated by Earth's magnetic field. And I like this quote so this is Alexander von Humboldt, and he wrote this fantastic book called Cosmos, where he tried to sum up all knowledge that people had at that time. And he was very interested in the magnetic field, and he has this quote: "The mysterious march of the magnetic needle is dependent both on space and on time, on the course of the sun, what the sun's doing, and its place on the surface of the Earth." So he already understood much of this and was very curious as to the origin of things. And we're, I think, part of this tradition, trying to, now with much more observations and more detailed modeling than he had, try to get to the bottom of these questions. Yeah, so that was a short appetizer for the things we're going to be talking about for the rest of the day. So what I propose to do now, going forward until we take a break for coffee, is to talk about geomagnetic observatories. So these are measurements that are made on the ground by dedicated instruments and observers trying to very carefully measure the Earth's magnetic field. So before we go in here, are there any questions, let's say, on this big picture that we've started with? No? So are you ready to go into the details now, right? Okay, let's do that. How are we doing for time? Yes. So we'll begin by talking about measurements of the magnetic field that are made from ground. So there are a number of types of measurements you can make from the ground. So the first one would be if I give you a magnetometer, you could walk around with it and make a series of measurements. So that's a ground survey. Typically, someone walks on a chosen grid. Usually, you're measuring the field intensity. And that's if you want to characterize some very local magnetic anomalies. Another possibility would be if you're on a ship, like the way they put out this ocean bottom magnetometers we saw, or ocean bottom seismometers that we saw earlier. Out on these boats doing scientific mapping of the oceans, they can tow a magnetometer behind them and measure. Again, there you're mostly looking at the spatial variations of the magnetic field. So another type of measurement you can do is you can repeatedly go back to the same place, let's say every year or every 5 years, and make a measurement of the magnetic field again. So this is called a repeat station observation. And so there you're trying to measure not just the field intensity, but also the directions systematically over many decades. So there are a number of countries that do this systematically, and that allows them to have very nice regional, national maps of how the magnetic field is changing in time. So let's say regional secular variation. So these are when you go to a certain location, but there's no buildings there's no infrastructure. You're just coming with your magnetometer, and you spend maybe a day or a few days making your measurements. But what I want to discuss here is rather very established observatories where people are making dedicated measurements of the magnetic field. So there's a worldwide network, I'll show you a map in a moment, of these observatories. And so what's crucial here is they're making high accuracy, absolute measurements. So I know some of you are working on space physics, and you are mostly interested in changes in the magnetic field, the variations. Now, if you want to study the magnetic field coming from the core, you need really the absolute level. If I want to look at how the field is slowly changing, I need to know the absolute level of the field. If there's a drift or something, that maybe doesn't matter if you're looking at high frequency things, that's a problem. So these observatories, they are really focused on absolute accuracy vector measurements. And they can be recording also variations, usually on timescales of seconds or minutes or hours. And some of these are very long records, going back to the time of, well, just after von Humboldt, time of Gauss, who was setting up a very important network of these observatories. So this is a map of the current network that we have of these ground observatories making these absolute vector measurements. And so you can see that it's certainly not uniform in space. That's because much of the Earth is ocean, and in fact it's very difficult to make magnetic measurements on the ocean. Maybe there's some ways using some tools like the seismometers that we just saw, but it's very technically challenging to do this, especially if you want to make absolute measurements of the vector field. The colors here are showing you, so these are all the stations that are reporting data, but they are reporting what's called definitive data or close to definitive data at different, with different amounts of delay. So the observatories have to use some time to check and properly calibrate their measurements. But so in this map, there's about 174 observatories operating, and 100 of these had reported definitive data from 2 years ago in 2023. 81 had reported definitive data from 2024, and just 76, the red ones, had definitive or close to definitive data from this year, from 2025. So this is a map that was produced by BGS, who are looking after the World Data Center and have a product called OXOBS that Ashley will show you later. So what's important here is not just the spatial coverage, but also how rapidly this information is being reported. If you want to know the present field for navigation, you need up-to-date information, right? And unfortunately, the distribution of the red points is not as good as the total distribution. So there are some challenges here. And I think this is where we have to work as a community to try to optimize and improve this as much as we can, okay? But it's, this is a serious work, yes?
How can you explain this decrease of the acceptable definitive data that is given by the observatories?
So it's not, I wouldn't describe it as it's always a decrease as you go close to present.
Yeah.
So it's not specific to just 2025. If we'd looked in 2020, you'd see a similar pattern. So it's about the amount of resources essentially that people have to be able to do all the processing and checking of the data and delivering that as fast as possible, okay? So yeah, I would describe this as a drop-off in the amount of available definitive data as you come close to the present time, right? Still, many places are doing a great job, but there's room, I think, to see if this can be improved, yeah. So what does one of these observatories look like? So I'll show you some examples now. So this is an example of an observatory from Heartland in the UK. So this is a typical, very well-established observatory from a country where there's a long tradition of making magnetic measurements. And so what you see here is that there's several houses, and these houses will contain different instruments. So some will be used for making absolute calibration measurements, some will be used for having a flux gate magnetometer that's continuously measuring the field. There'll be other houses with electronics devices, and you can see they're all separated, and all the buildings are well away from any other sources of magnetic interference. So that's the kind of, I guess, ideal setup, if it was possible. So this is an observatory that I've been to in the west coast of Greenland. So that you can see the icebergs in the background. So this is a little bit less high quality building infrastructure, but still we have houses where the different instruments are kept indoors, and we have heaters to try and keep the temperature reasonable for the instruments to be operating. So this is an example of a more remote observatory. And finally, here's a more modern example of an observatory that was established in the 2000s on Tristan da Cunha by Jürgen Matzke and his colleagues. So here you have just a few essentially boxes that are tied down because it's very windy. So this Tristan da Cunha, this is a rock in the middle of the Atlantic. We're very interested in what's happening in the South Atlantic because the magnetic field is weak there and it's changing quite a lot. So Jürgen and colleagues decided to set up this observatory there and tried to keep everything in a way as compact as possible. So there they just had one house and then one other container where the continuous measurements of the magnetic field were being made. So if you look inside here, so inside this smaller house, you'll see that there's some polystyrene insulation to try to keep, again, the temperature constant. And sitting inside there is the main 3-axis magnetometer measuring variations of the magnetic field. So trying to keep the temperature constant. In the other larger house is where we make absolute measurements. These are the calibration measurements that need to be made about once a week to make sure that the data from the continuous variations is being calibrated. So this consists of 2 instruments. This thing in the top left corner is a proton magnetometer that's measuring the strength of the field, and this is a theodolite which has a single axis flux gate instrument on it that then you move around to try to find the direction of the magnetic field in the horizontal plane and in the vertical plane. So once a week you have to come and do this manual measurement to then calibrate what's going on here. And what's very important is this has to be protected against the weather, which can be really extreme. Ideally, you'd like it to be cheap to set up, cheap to maintain, and you need to be very careful to put these instruments on pillars that are very stable. You don't want these pillars to be moving, for example, if the Earth is moving. So you need to bed this deep into some bedrock or concrete it down into some hard rock, and then you site your instruments on top of these. And it has to be free from large magnetic anomalies, no big magnetized rock right below you, hopefully, and any kind of electrical currents from man-made things. Especially if there's any DC currents, they're bad news. So things like train lines and trams and ooh. But Tristan da Cunha, that's not the problem. It's, there's not that much out there. Okay, so now I'm going to go a little bit more detail in these instruments. So we measure the strength of the intensity of the field using a proton precession magnetometer. There are other variants on this that could be used to measure the strength of the field. But this is basically a quantum physics measurement. I'll explain how it works in a moment. It gives absolute accuracy and it measures the field strength. The other type of instrument that's being used, and it can be housed in different ways, is what's called a flux gate sensor. So this involves essentially two coils around a piece of magnetic material of very high susceptibility. And so this one gives you accurately the direction of the field, but it's not absolute, right? So this can drift, this can change with temperature, and it has a scale value, an offset that you need to determine. So that's why you need this combination of the one instrument is not enough to get this absolute accuracy measurements. So the proton precession magnetometer. So this is essentially a quantum mechanical effect. And what you do is you're measuring a frequency, and that frequency you can turn into a magnetic field strength. And because it's a frequency measurement, that's very easy to do. You have some signal that's oscillating, and if you have GPS time, you can very accurately then determine the frequency of that signal rather easily. So the basic physics that's involved here is the precession of protons. And so if you have a proton that has its own magnetic moment, and that is experiencing a magnetic field that's not aligned along its moment, it will oscillate, it will precess, okay, at a certain frequency that depends on the strength of this magnetic field, right? And the frequency of this precession is related to the field intensity F by a constant, gamma p, and that's a quantum mechanics constant, the gyromagnetic ratio of the proton. We know that, right? So if you measure this frequency, you get F, right? So this is very simple, and that makes it nice to measure. In practice, what happens is that you have a container, usually something about the size of a can of soda, about 300 milliliters, contains either water or alcohol, and around that is wrapped a coil. And what happens is that initially, before you have any current in the coil, all the protons in this liquid are aligned with the Earth's magnetic field. Then you drive a current through this coil, right? That's a strong magnetic field. So this then forces all these magnetic moments to line up with the axis of the coil. And then you switch it off, right? Switch off the thing in the coil. Now it's got the Earth's magnetic field again. But now these protons are not aligned with the Earth's magnetic field. So they're going to precess. and they precess at this Larmor precession frequency. So that's how these proton magnetometers are working. So in practice, you get a waveform out that looks something like this. So it will be oscillating, and you have to measure the frequency of that, and then you can determine from that the intensity of the field. And for the type of windings that you typically have in these proton magnetometers, for the strengths of the magnetic field, either at low latitudes, at high latitudes, at 25,000 to 65,000 nanoteslas, you're looking at about 1,000 to 2,000 hertz. So it's rather high frequency, so you can get a lot of oscillations and get a good handle on this frequency. So it's a very robust, nice measurement. Okay, so that's the simple one, the proton magnetometer. The other type of measurement we make is with this thing called the flux gate magnetometer. So this is measuring the magnetic field along a sensor axis. So that's what's shown here is one of these sensors. So inside this there are two coils, one where you're driving a oscillating current, alternating current, and a second coil which is then measuring the changes in the magnetic flux that are going through the core of the flux gate, which is a material that is very easily magnetized. Okay, so it's called flux gate because it's all about the amount of magnetic flux that is being kind of focused through this coil, this core of very easily magnetized material. So this is the basic setup. You have these two coils, the driving coil and the pickup coil, and in the absence of any external magnetic field, what happens is that as you drive through the driving coil, you magnetize the material inside the core. So this is a hysteresis curve showing the magnetic field that is coming out of the instrument against the applied magnetic field. And what happens is if you don't have any external field, you get just a simple oscillation here, because it doesn't matter whether you're in the part of the cycle where the magnetic field being driven is in this direction or in this direction. It's all the same. But if you then come with an external magnetic field from the Earth, that then gives a bias here. So now it's going to be more easy to drive the material in the center to saturation in one direction than the other. So that means you get a small asymmetry here. So here the dashed lines, it's not just an oscillation now, it goes up and then it's flat, and then it's down, and then it's up, and then it's flat, okay? And so that's the magnetic field that's through this coil, and then the voltage that is picked up in the pickup coil is about the derivative of this magnetic field. And so what happens is that you get a second harmonic here when there's an external field that is directly proportional to the strength of the magnetic field along the axis of the coil. Okay, so that was fast, but I hope you get the basic principle. It's all about having some easily magnetized material in the middle, and then the Earth's magnetic field is breaking the symmetry along a particular axis. So this kind of flux gate coil is then mounted on a theodolite. And why a theodolite? Because there you can very carefully move it and measure angles very precisely. So very special theodolites that are non-magnetic are built, and then they have these flux gate sensors mounted on them to make absolute measurements of the declination and inclination. So usually what you do is you try to find, first of all, let's say in the horizontal plane, so you'd level this, the theodolite, and then you would look to see where the signal coming from your flux gate goes to zero. And when it goes to 0, you're orthogonal to the Earth's magnetic field, right? So that then tells you the horizontal direction of the magnetic field. And then if you know the direction of magnetic north, that gives you this declination angle. And once you have the horizontal direction right, then you can tilt it in this plane and find again where the field is going to 0, and that gives you the dip, okay? And there's some tricks here, because if you have any misalignment between your flux gate and the axis of the theodolite, that can give you an error. But if you make these measurements with the flux gate both above and below the telescope here and the theodolite, so you basically turn this around in a number of directions, and then that can get rid of these possible systematic errors that you can get from a misalignment either in the vertical plane or in the horizontal plane. So that's how essentially you're measuring this declination and inclination. The other way these flux gates are used is in these so-called variometer instruments. So these are where you have 3 of these flux gates in perpendicular directions, and usually they're embedded in a big cube of marble. And why marble? Because it's very stable to temperature changes, right? So these, you don't want the directions of these 3 coils to move with respect to each other. So you put them in a big cube of marble, and then you hang it. This is a suspension here. And then you leave this thing, and then you just let it record, okay? And that is giving you the magnetic variations in 3 different directions, let's say on timescales from seconds up to as long as you can measure. But then you have to calibrate this one with the proton measurement and the DI manual measurement, okay? So the nice thing about this is it's nicely stable in the long term, provided you can make these calibration measurements that I mentioned. Okay, so the basic way this is working in terms of how you get data, so you're all people who are interested in the data. Now I've told you really the measurements. These measurements, I would say, are very important. If these are not done right, you can't do science, right? So it's worth really knowing about them and respecting that these are very important. So what happens is that these data measurements, the variometer measurements and the calibration measurements after the calibrations have been applied are then passed typically from remote observatories. For me, for example, for our group, it could be up in Greenland. The measurements are then coming back to a central observatory where all the calibrations are carefully applied, and we get what's called the baseline that is needed to get definitive data. And then this data is then sent, could be to industry. So that could be for people wanting to do high accuracy drilling, or it could be European Space Agency. And then at the same time, it's being passed to international organizations. Intermagnet is a kind of club for the observatories where they make sure that the data has been produced correctly. So there's a checking procedure done. To be a member of Intermagnet, you have to do things correctly. Okay, and then once this checking has been done, then you get this definitive, close to definitive data, and then this can be passed out into things like the World Data System and out for everyone to use. Another route here is through IAGA. We can then produce indices, all based on this data. These indices, for example, of magnetic variations, things like the KP and DST index that you may have heard of. Yes. So that's the flow of the data. And once you have these measurements over long periods, you can do things like track. So this is a plot showing how the declination changed in Copenhagen, where I'm working, going back from the 1500s. So people were making these measurements of the magnetic field direction even a long time ago. And this magnetic declination, the angle between the local horizontal component of the magnetic field and the geographic north. So this was 10 degrees in Copenhagen 500 years ago. And then it went positive 10 degrees, then it went through zero, then it went down to about minus 20 degrees about 200 years ago. And today it's actually just gone through zero again, and it's about positive 4 degrees at the moment. So you can only track these very long-term changes with these absolute measurements. This is a similar plot for the magnetic inclination, so the dip. So that one has systematically decreased actually in Copenhagen and then flattened off. So if you're interested in studying these long-term changes from the core, you can do it. You can also look at more rapid variations. So this is 1 year of data from an observatory close to Copenhagen. So each row here is 1 month. So this is January, February, March, April, May, June, down to December. And this is now the northward component, the X component that you asked about before. So you see again, as we saw from the NIMENC data before, you get typically these daily variations. They're never exactly the same, but there's some common pattern from day to day. And then very occasionally you get one of these large solar-driven disturbances, okay? So this is what the data over a year looks like. And there's clearly some similarity from month to month and day to day, but then on certain days, more exciting things can happen. So one question that I would like you guys to talk about over your coffee break, because later today, we're going to think about satellite data and observatory data. And in fact, they both have advantages and disadvantages, but it's important to think about what each is good for. So think about, given what I've been discussing with you, what are the advantages of this observatory data? Think about all the hard work that's done in producing very accurate measurements, right? And long time series and other things, right? Also, what are the challenges of using ground observatory data to study the present geomagnetic field? Are there any shortcomings here? So have a think about that, and I'll come back to you to hear your opinions about this, okay? So the last point I want to mention before we take a break is that an important product that's coming out of these observatory data is these so-called magnetic disturbance indices. And this is very useful for studies of space weather and space physics. And I have the impression that some people are using these indices and they don't really understand what they are. So I would like to really clarify to you where this is coming from. It requires these good observatory measurements, okay? So the first one we'll talk about is DST, right? So what is this? This is called the Disturbance Storm Time Index. So maybe first of all, what's an index in this context? So index is usually a number that you use to track something. Like people who are interested in the stock market and so on, they have an index that tracks what the stock market's doing, right? This is not an index for the financial system, it's an index for the geomagnetic system, right? So this DST is designed to be a measurement of geomagnetic disturbances, specifically those produced by this equatorial ring current. So there's this out in the radiation belts, the Van Allen radiation belts that are at something like 6 to 10 or 6 to 30 maybe Earth radii. There's an inner and outer radiation belt. So there you have trapped particles that are moving and they're producing a current that, at least a first approximation during quiet times, is approximately symmetric. So in this DST index, we try to make a combination of the ground observations that tracks this thing and its time dependence. So how this works is that you look at 4 low latitude observatories: Hermanus in South Africa, Kakioka in Japan, San Juan in Puerto Rico, and Honolulu. So four stations. I think I have a map of these. Yes, so this is this red station. So Hermanus, San Juan, Honolulu, Kakioka, right? So they're all at different longitudes and at fairly low latitudes. And so what you do there is you look at the disturbance in the horizontal field, right? So the horizontal part of the field, you remove the slowly varying core field part, you remove the daily variation part, and then you average what's left between these 4 stations. And you do that on hourly mean data, and then you have this DST. Okay, and when something dramatic is happening on the sun, and the energy gets transferred into the particles in the radiation belt, they will produce a much stronger current, and you'll see that very clearly in this DST index. So this is an example that I think is close to what was mentioned earlier. So this is an example of what's happened during a storm in March 2015 for this DST index. So what happened was that there was a sharp onset where it went positive, and then it went within a few hours strongly negative by hundreds of nanoteslas, and then there was a recovery over several days. So tracking this kind of magnetospheric current system you can get from the ground observatory data via this DST index. The second, probably very classical index that people talk about is called KP. So this is a kind of global measure of how disturbed the Earth's magnetic field is. So I said things are quiet when you just have this simple daily variation. So how this is measured, what you do is you look at the range, which is the difference between the highest and lowest values during a 3-hour time interval. And you do that for the 2 components of the horizontal field. So the northward component, the eastward component. You take a 3-hour time window, and you look at the largest difference over that 3-hour time window, and then you take the largest of those 2 numbers in either the northward component or the eastward component. And that gives you some number at your 1 station for what's called, that's a local disturbance in nanoteslas, right? And then there's a scale that for each station you can use to convert that disturbance into what's called a K index, which goes between 0 and 9. So this thing, it's kind of a quasi-logarithmic scale. So you know logarithmic scales from seismology, from the Richter scale. So 0 is very small, and it gets bigger and bigger as you go larger, but there's a very big difference between the 5 and 7, for example, as you get to the higher end, right? So then now you've got one of these local K indexes for each station, and they are expressed in scales of thirds. So you can have 0, 1, 2, 3, up to 9, and then you can have plus or minus in between here. That's the way these things work. And then to get from these Ks that are for each station, you can then average them over 13 stations to get KP. So P stands for planetary, right? So you're taking now data from 13 stations. Now it's said to be global, but it's the green stations here. So you see that they're mostly in North America and Europe. So global with a pinch. Yeah, this was set up in the 1930s when there was not really good distribution. So there are 2 stations only in the southern hemisphere, in Australia and New Zealand. So you're looking again at this range disturbance at each station within 3 hours, seeing the biggest change within this 3-hour interval, and then that gives you a number at each station, and then you average those to get KP. So that tells you within a 3-hour interval, are things changing a lot? So these indices, from my point of view, studying the internal field, I want to use them to say things are disturbed, and I don't want to use the data. But some of the rest of you might be very interested in those times, right? But again, it fundamentally comes from these observatory measurements. Okay, so I want to finish there for now. And I think we should take a break.
Just to orientate you briefly, you should have, you're looking at 2 different pages. This one, at book.magneticearth.org, you'll see these series of notebooks. So for the moment, we're just going to look at this first one here. But there are other ones, but don't worry, we're not going to do all of these. We're just going to focus on a couple of them. And you can scroll down and you can see the whole notebook there, and see what we're going to look at there. The other thing is, if you go here, the rocket at the top, and then there's this button, Jupyter Hub. So when you click that, that is going to load the notebook. So you can use the first web page just as a reference to see what it's meant to look like when you run it. So if you change anything within your live notebook, then you will not get so lost, because you can refer back to the web page where it's pre-run. Yeah, but yeah, also on these pages, some of them I've hidden the code. So when you're in the live notebook, that won't be hidden, but just to present it more nicely on the web page there, those bits are hidden, because the focus is really on looking at the science, looking at the visualization. Okay, there's code there that you can just run right away, but you don't need to write too much necessarily, but you have the live Python environment there where you can do whatever you want. So how many people are familiar with Python first? Yeah, most people, almost everyone, yeah. But, and Jupyter? Most people, yeah. Okay. So, yeah, so if you will open the notebook now, I'll make it a little bit bigger. Yeah, so if you're not familiar with Jupyter Lab, you have a file browser on the left here where you can navigate around to find where you are. But when you click that magic link from the other web page, that will take you directly into this notebook.
I have a question, because we have the
Yeah.
folder called shares,
Just ignore that.
but I don't have the other folder.
Okay, so if you could go back to this page. Yeah?
Where is this?
Okay. So just type this URL in. Yeah. Yeah. And then from there, you can go here and click on this. But select the notebook on the left there. So has everyone got to this stage? Yes? Okay. Right. So yeah, you have the file browser on the left, so you can, yeah, we're looking at this one here. You can open multiple notebooks at once if you want. You can close them and open them again You can put them side by side if you drag them like that. You also, if you click the plus here, click the plus there, it'll open up this launcher. And from here, you can access a terminal. And you can also create new notebooks. So when I create a new notebook there, that's here. And you can organize your files with the file browser. So once you're in here, you can run cells by clicking this button, select a cell, and then click run. So you can proceed through, and then, so this first bit, just importing some packages, and then we're going to load some of this intermagnet data from one observatory. So there are multiple ways you can get intermagnet data. This is a system we have set up for this VIRES service. So VIRES is a software that's developed to support Swarm, but we also have this ground observatory data as well there, because it's useful to use both at the same time with the same interface. So don't worry too much about the code itself. It's simply accessing the server and downloading. And select the observatory here and which years of data we're going to access. And the cadence is M is for minute. So we're taking 1 minute values from this observatory ESK, which is Eskdalemuir in Scotland. So when you run that, that's going to go to the server and download the data and load it as pandas data frame. So you see here, time, position, and the 3 vector components. So this next cell, I'll stop in a minute to check everyone's getting on okay, yeah. So this next cell is going to make an interactive tool that will allow you to play around with that data. So you just click run, and then you should have this. So you can select the time range here, so the beginning and the end that you want to inspect. So here we're looking at just 1 month, so the January 2003. And the first thing you do is maybe untick these boxes. So this is the original 1 minute data. And so you have 1 month here and a lot of things in between related to the daily variation and some geomagnetic activity. So there's signals that you can see here from the ionosphere and magnetosphere. And then you can take out a bit of that noise by evaluating the hourly mean here, so you have a smoother line. And the other one, the other box there, is going to show the offset from the annual mean. So if you take the whole year, take the mean, that's showing the offset from that mean across the whole year. So there's a few questions here. So looking at 1 month of data, what signals can you observe? So this is 1 month here, and well, I've already said it, it's this ionospheric and magnetospheric signals. Sorry? Yeah, sure. So, each day is about here, so there's a kind of thing, you see it better here. Yeah, sinusoidal variation as we're moving through the ionosphere as the Earth rotates. So you maybe see it better if you zoom in on just one day. Oh. Yeah. So you can browse through and just look at one day at a time if you like. But I'll leave you to play around with it a little for a while just to get a bit of familiarity with this data. Yeah, and then there's a second question there that you can answer in a minute. So you can look for this quieter week. So we yeah, just select the first week. It's not entirely quiet. There's some things going on, but if the next thing you do is look at a very stormy week, this time period here, then you should see a big difference. So just looking at the question 2 there. So here's a quieter week, and you see the typical variation there is what's that? Like 50 nanotesla. So that's the variation you get over a day can be around 50 nanotesla. That's similar in each component. But then if you look at a very stormy period, this is what we call the Halloween storm because it happened around Halloween. Now look at the scale here, it's completely changed. So this is, over 1,000 nanotesla, so it's many times larger. Yeah, if you look at KP, it'll be yeah, the KP is this 3-hourly window looking at how disturbed it is over that 3 hours. So if you look at KP for this event, it'll be
9 or so.
Over
8.
9.
Yes.
9 is like the maximum. Yeah. So this last question here, expand the time window to display all of 2003. So if I just select back beginning of January and end of December. Yeah, so you can see here the event we were just looking at in October. It's way bigger than the whole of the rest of the year. And again, you can take out a bit of that variation by looking at these hourly means, and then you can show the offset from the annual mean. So if you look very carefully here, I mean, you see it more in the Y component. In the beginning of the year, it's more below this line. So the line through the center here is the annual mean. So we're highlighting the offset from that mean. So the beginning of the year, it's a bit below the line. Towards the end of the year, it's more above. And that is that slowly changing signal from the core. So, but, in amongst all of that, lots of variation. So if you're trying to model the core field, you're just trying to pick out that line, basically, and throw away all this other variation.
So in fact, some of the very early satellites that were sent up, one of the early Sputnik satellites from Russia even had a magnetometer on board it measuring the magnetic field from space. The first really serious scientific surveying from space was carried out by NASA in the late 1960s. And in around 1980, there was something called the MagSat satellite. And this was the first satellite that was making vector measurements of the magnetic field from space. Earlier, it was just measuring the field intensity. And since 1999, there's been a series of survey satellites, the Danish Ørsted satellite, the German CHAMP satellite, There was an Argentinian satellite called SAC-C, and especially what we'll focus on here is since 2013, the SWARM trio of satellites have been launched to survey Earth's magnetic field from space. So you see here the dates that these are operating and the altitude. So these are in what's called low Earth orbit. So typically some 300 kilometers up to maybe 700 or 800 kilometers. Also, we'll talk later, there's recently been a Chinese satellite, Macau scientific satellite, that has been launched that's also making very high quality magnetic measurements, but from a different type of orbit. So it's only covering mid and low latitudes. There are also, in terms of measuring the magnetic field from above the surface, aircraft surveys. So, but typically these are only done on local or regional levels. So they're flying typically maybe 100 meters or maybe up to 1 kilometer in altitude. And that's really for measuring these local anomalies rather than getting the global field picture. But I'm going to focus here on these so-called magnetic surveying satellites that are really focused on making the best possible measurements you can from space, absolute measurements of the magnetic field. So this is a picture from my colleague Niels Olsen that collects images of many of these satellites. And one thing that they have in common is that they typically have a long boom. And the magnetometers are set away from the body of the satellite where there are solar panels and then currents happening, and you don't want to be measuring those. So you typically have a boom which can be, well, as long as possible, so get you as far away as possible from the body of the satellite. Part of the challenge with these booms is you have to get them up to space and then somehow get them out. So there's been different ways of unfolding it. With this Ørsted satellite, they had a telescopic spiral coming out. In SWARM satellites, which are shown here, the boom was folded up, and then when it got up, the boom folded out. So we have now, at the moment, the main satellites that are currently measuring the magnetic field would be the 3 SWARM satellites. So there's a lower pair. So they're a pair. That's useful because if you look at the difference between the measurements on the 2 satellites, you get some information on gradients in the magnetic field. And a 3rd satellite that's higher up, that is sampling a different position with respect to the sun. So that can be useful for distinguishing currents in the magnetosphere and ionosphere compared to from the Earth's interior. This is a satellite CSCS. This is the Chinese seismological survey satellite. This was launched in 2018. This provides good intensity measurements, also vector measurements, but the vector measurements are not so high quality. And this is this MSS, this Macau satellite that was launched just a couple of years ago. So I'm going to talk especially about SWARM and a little bit about Macau satellite. This next picture is showing you the altitude of these satellites as a function of time. Starting in 2000, we had the Ørsted satellite, which is shown in green. So it was higher up at about 750 kilometers. And then in 2001, we had the CHAMP German satellite that was launched, and it was at a much lower altitude. And it was operating essentially for a decade. It re-entered in 2010. Then we had a gap shown in gray here, and then the SWARM satellites were being launched in 2013. So the altitude here is important. The lower altitude you're at, the closer you are to Earth's surface. That means the easier it is to study the core field and the lithospheric field. So if you're interested in these internal sources, you want to be at as low altitude as possible, right? The challenge is if you're at very low altitude, there's drag, and then sooner or later you're going to re-enter, right? So you can't stay very low for very long. So it's some kind of balance. You want it high enough so it stays, but low enough so that you can get really high resolution. So there's some other satellites mentioned here, GRACE, Cryosat-2, this is GRACE follow-on. So these are ESA satellites which carry magnetometers, but they don't make absolute measurements. So these are measuring the variations in the magnetic field. And if we have another satellite around at the same time, like CHAMP or SWARM, we can calibrate the data from these satellites remotely. So we can use this data as well, but it's not the same quality as Ørsted, CHAMP, SWARM, and MACAOSat. How steep these lines are for the descent, it depends on what the sun is doing. So at the moment, they're all descending quite fast. So this is 2025, MACAOSat and SWARM. They're all going down quite fast. That's because the sun's been quite active over the last year. So how long these satellites are going to continue, that depends largely on what the sun is doing. So I thought I'd show you a few pictures about the launch of SWARM. So SWARM was launched in November 2013, and the 3 satellites were launched together from Russia using some very old Soviet era technology. So these are old Soviet ballistic missiles, and the 3 SWARM satellites were packed together and put on top of this launcher. And these were all these 3 eggs in one basket, right? And there'd been some problems with this launcher previously, and we were very nervous that everything was going to work smoothly because these were very special one-off satellites. But the launch went smoothly, and the 3 satellites that were packed together separated as was planned. And you can see here the booms have not yet been folded out. And the booms folded out, and here is a view of the SWARM satellites where you see the key instruments. So this is this boom away from the body of the satellite. At the end of the boom, we have an instrument measuring the intensity of the magnetic field. So this is a scalar instrument. Here, sitting in the middle of the boom, we have a vector magnetometer. So again, one of these flux gates, just like we talked about in the ground observatories. So it's got 3 perpendicular coils. And what's very important here is you need to know which direction your satellite is pointing for these vector measurements to be useful. So what we have here is 3 star cameras. They're looking up at the stars, and we have catalogs of the stars, and by looking at an image of the stars, it's possible to tell what direction the satellite is pointing at to very high accuracy. So this is how you know what direction the satellite is pointing. That means that you can interpret these 3-axis vector measurements properly. So these are the key instruments. So this is a side view of one of the SWARM satellites. So I've mentioned this absolute scalar magnetometer, vector field magnetometer, and it's attached via a very rigid optical bench here to the star trackers. You don't want any rotation of your star trackers compared to your magnetometer. If there is, then you're going to get an error in your orientations. On the body of the satellites, we have solar panels providing the power. We have GPS and some other instruments. We have a laser reflectometer for ranging, an accelerometer, and some S-band antennas. So those are the main. Yes, please.
What is the absolute solar magnetometer is far further by
Well, yeah, I guess that was a choice. You don't want these 2 things should not be too close to each other, because then they can disturb each other. So you need them far enough apart that they're not disturbing each other. And I think the absolute scalar instrument, in a way, this is the key to the calibration. So you probably want this one to be really accurate, right? So that's, and I guess it's, There's probably some mechanical stability issues if you put the big heavy thing at the end as well, I would guess. Right, so I think that's why. Yeah,
If this is moving through the field, there will be induced current.
yeah,
So how can it be?
It's a very good question. So the short answer is that has to be characterized and corrected for. You try to minimize it and then you try to characterize it on ground and then you correct for it. I'll actually mention that in a moment. But yeah, so there is some currents induced in the satellite and they really have to be corrected for the data to be high quality. Yeah. Even though it's some meters away maybe from where the key instruments are. Oh, sorry. Yeah.
So it's more a question about the access of the data because of the situation now with Russia and other countries.
Yeah.
Do you have problematic with some work that you have in common or for sharing the data, for having data access? Is there any block?
So for ESA, all the data, as far as I know, is completely open to everyone from all countries. So that's the policy for ESA is to make the data freely available. You might have to register, but that's just to collect some statistics. Everyone has access to the European data. US, Canada, Russia, China, whoever, right? So I mentioned Russia because of the launcher, but this was not a collaboration, this was a payment situation.
Okay.
So you paid for the service to be launched. Just like today, you could pay SpaceX or someone else to launch. In those days, it was cheaper to do it that way.
But did you get any problem to get data from, for example, Russia observatories now? Or
Yeah, now with the ground stations, that's a much more tricky issue. So there are, I don't know if anyone else wishes to comment on this, but I mean, as far as I know, there is a delay with some of the data from the Russian stations. So there are Russian stations in intermagnet, but Kieran, maybe you know more about that.
Yeah, so the Russian observatories just stopped sharing their data. They can upload it to the Int'l website they wish, and there's another World Data Center. And then a lot of observatories cross-check their quality, so you'd send your data to a different observatory to check. And a lot of people decided not to engage with Russian observatories to check the data anymore. So that meant that it hasn't been officially uploaded because it hasn't been able to. That situation. There was an AGA resolution about data sharing, so we do try and be open in terms of science and all that, but obviously it's up to people's conscience as to whether they want to engage or not. So, but yes, some countries just don't submit data to the World Data Center, and actually China, for example, has lots of observatories, but they really contribute a few overall. I think so. But that's on per institution level because they're all run by different institutes. So it's really up to the institute as to how the data Rob is a lot more open in Europe as sharing data. That's just historic rather than.
But I think as scientists, we want to share data because that's the way science advances. But of course, there's politics involved as well. So it's complicated.
For example, in the US, the situation, a lot of the observatories have low staff, there's a better employees, so we're now starting to see a decline in quality there, for example, so that's something to do with embargoes, or that's just staff issue. This does require constant staffing to get quality. And that's something that you dedicated lots of great data off internet. Actually, so it's all free available, but it hasn't cost it. Because somebody has to pay for that. Typically, the taxpayer would not just
Okay, I think we should move forward if we want to get to lunch. The discussion is interesting. This swarm mission, it involves 3 satellites. So as I mentioned, there's this pair that's flying separated by about 150 kilometers. Now, they're not exactly flying side by side. Does anyone know what would happen if these two satellites were flying exactly side by side? So there's, you see they're a bit offset here. So what would happen up here? They would collide, yeah. So they're slightly offset from each other, but if you delay the data by about 10 seconds, then they're more or less east-west. And then the third satellite is at a different altitude and a slightly different inclination. So what happens is the plane of the third satellite is moving with respect to the other two. So sometimes it'll be orthogonal and sometimes they'll be coplanar, depending on where you are over the 10 years. Yeah. So, and in just one day, so this was in a situation where they were almost orthogonal. So this is one day from 2018, in October 2018. I showed you this earlier. So this gives you an example of the kind of coverage you can get with these three satellites under this, I would say, optimal situation where they're well spread out. So it's not full global coverage. There are gaps, but it's, and there's also a gap at the pole because they don't go right over the pole. Yeah. Now we come to the question that was mentioned a moment ago about corrections. So there are these things that we call stray magnetic fields. So these are intrinsic to the instruments and the spacecraft body, and we can basically split these into different categories. Things that are static, because there are parts of the satellite that are essentially permanently magnetized, or maybe they have a magnetic field when the satellite's doing a specific operation. So that's a state or operation dependent field. Then we have induced currents that you mentioned. These can happen due to various things, also including the solar panel array, things like battery charging, or we have things called magnetotorquers, which are used to maneuver the satellites. So depending on what these electrical currents involved with these processes are, there will be signals from these. And because some parts of the satellite are soft magnetic materials, if you apply the core magnetic field to these, they get magnetized, right? So all of these things, they can be characterized on ground and measured in a controlled situation, so you know what they are. So we have a model of these stray magnetic fields that for a given orientation of the satellite with respect to the internal field, we know what they are, given a certain operation of the satellite. So those things have to be corrected. And a lot of time was spent developing those correction models. In addition, on Swarm, after it was launched, it was found to be a stray disturbance field that wasn't actually expected. And this depends on the angle of the sun on the satellite. So it turned out that there was a thermal gradient across the satellite, especially when it was going from shadow to sunlight. And this thermal gradient was giving a potential difference. There was a thermoelectric effect. And it turned out there was a grounding wire on the outside of the satellite that formed a loop that then gave a current. And this current depended on the solar illumination. So that disturbed the data, but it was systematic. And over some years, the colleagues Vincent Lesueur and Lars Tuffner-Clausen have characterized this, and this can be corrected for. So these satellites, some work is needed also on that side to get really high quality data. And it's not so easy to go up and rearrange things or fix them. Once they're up there, they're up there. But you have a lot of data to try to characterize any biases. A few words about the instruments. So this is the absolute scalar magnetometer that sits on the end of the boom. So it's not exactly this proton precession magnetometer that we talked about earlier. So this is based, it's also a frequency to magnetic field strength, quantum mechanical effect. This one, it actually exploits the Zeeman effect. So here, again, you're measuring some frequency, and there's a fundamental constant. It's related to helium in this case, that then allows you to get the field strength. So essentially what happens here is that you have some helium atoms and you excite them by means of a radio frequency to what's called a metastable state, and then having a magnetic field, it splits the energy levels by something called the Zeeman effect. And then you can use a laser to pump some of the helium ions to a higher state, and this leaves a kind of gap here. And then you can, by applying a radio frequency, you can look at the transition between these Zeeman split levels. So this allows very accurate and also very high frequency measurement of this field intensity. So the main advantage of this is that it can be done to get very high frequency measurements of the absolute field strength. So it's a bit more advanced than this proton method, but it's based on fundamental quantum mechanics. And just to give you an idea of how the data processing works in these satellites, so to get the data that you actually use and Ashley will look at, you have basic engineering level data, and then there's various things that are done here. There's outlier detection and rejection. There's corrections for these stray fields. Then you have some additional adjustments related to filters that are being applied. And then you're interpolating things to seconds. And then you get the data out that you actually want to use. So just to be aware, there's some things happening behind the scenes to make the data that you're using nice and suitable. Moving on to the vector magnetometer. So the crucial flux gate involving these coils is sitting here. This thing, it's about the size of a baseball. It's spherical, and it has windings in 3 perpendicular directions. And then it's sitting on this thing, which is this rigid optical bench. And then these are these star cameras that are giving the orientation. And this is a similar picture of this processing for vector data. I'm not going to go through all of this, but just it's a bit more complicated because you also have to take into account the star tracker and corrections for it as well. Okay, so one thing that's important to know is how this calibration of the vector magnetometer is done. So what happens here is that the instrument is giving you some uncalibrated output, a vector, let's say that's got components E1, E2, and E3. And they're in engineering units. And what you'd like is the calibrated vector magnetic field, B1, B2, B3. So this is this BVFM. And you can show that this is related to the engineering measurements through this system. So there's a vector here, little b, which is basically offsets to the 3 axes. And you have a matrix S, which is diagonal. And this has got a kind of scale factor for each of the 3 directions. And there's another matrix P, which is taking account of the fact if your magnetometer axes are not exactly orthogonal. So there are 3 parameters that describe this so-called non-orthogonality. So in the end here, you have 9 parameters that are defining that you need in order to go from engineering units to calibrated vector measurements. So what you do is then you determine these 9 measurements by asking for the absolute value of your BVFM to match the measurement made by the scalar instrument. So that's called a scalar calibration. So what you do is you set up a least squares problem, and it turns out when you're doing this from many, many different orientations over the sphere, even just having a comparison to an intensity measurement, you can determine all these 9 parameters. So it's a very overdetermined problem. You've got lots of data to determine these 9 parameters, and then once you've determined it, it's calibrated. In practice, these things change slowly in time, so you gradually update this calibration. So that's why you need the scalar measurement in order to determine these calibration parameters. Yes. So that's a bit on Swarm. I wanted to briefly mention the other key satellites. So today we have this Macau scientific satellite. So this was launched in May 2023. So it's initially at about 450 kilometers altitude. So that's similar to Swarm. Swarm's altitude typically is about 500 kilometers for the higher one and maybe 450 for the lower two, although they're now all descending. So Macau was at a similar altitude, but it's at 41 degrees inclination. So it's not going over the poles, it's turning at about 40 degrees latitude. It has exactly the same flux gate instrument and same star trackers as Swarm, and it has a scalar magnetometer. It's a slightly different principle, but it provides, again, these high accuracy intensity measurements. And they are having calibrated vector data from November 2023, and this is being made openly available. You have to register, but with about 1 month delay, you can get the data. So you have to, if you go to this web page, you'll find out more information about the data from this satellite and how to get access to it. So what's shown here is that the data from, this is from a 4-month time window after I've done some selection to keep only data suitable for looking at the internal field. So you see there's really no data in the polar regions, but at low latitudes there's a very nice coverage. And what's nice is that the direction of these orbits in the Macau sat, they're more east-west. The Swarm orbits are much more north-south. So what happens is that you often have the Macau satellites' orbits crossing the orbits of Swarm. That's very useful. So you can try to fit this Macau sat data together with the Swarm data, and you can show that they are agreeing to within about 0.5 nanotesla. That's really good. Okay, so things are working very nicely with this combination of now 2 completely different missions. I mentioned before that there were also a possibility of using satellite data from other magnetometers and other satellites that weren't really designed to measure the magnetic field. So an interesting one is this Cryosat satellite. So that's a satellite that's mostly designed to look at changes in the ice in the polar region. But on board, it has a very good magnetometer and it has a very good star camera. But it does not have one of these scalar instruments. And that was launched in 2010 and it's still operating. So in fact, it actually covers, in a way, this gap between Champ and Swarm. It's a bit higher. It's about 700 kilometers altitude. And what's nice is that it has housekeeping data available. So you know things about when the satellite was doing things like magnetotorquers were firing, what was happening with the temperatures of the magnetometers. So it's possible for this satellite to solve, again, for these calibration parameters. If we have another satellite around that's measuring the magnetic field, like Swarm or Champ. And so you can characterize, so there are more disturbances on these non-dedicated missions. So there's no boom here. So that means the magnetometer is on the body of the satellite. It means it's going to be noisier, right? But we can still get some useful data out of this. The RMS of the data here for Cryosat 2 is something like a scatter of about 5 or 6 nanotesla compared to maybe 2 nanotesla for Swarm. So yes, good to be aware of this. So now with all these satellites together, it's interesting to see what type of coverage we have. If we just look at one time, so this is from work by Alexander Greiver, who's going to be lecturing tomorrow. So Alexander and colleagues have looked at what happened during this storm in May 2024. So this is during this storm. And what's shown here are the orbits of all these satellites and the ground stations that were available. So the red dots are the ground stations. So blue is swarm A, red is swarm B, and swarm C is more or less the same as swarm A because they're flying side by side. Then at low latitude, the yellow thing here, this is the MSS satellite. There's an offset here. That's because it's showing one orbit. The Earth has moved after this one orbit, basically. And then with these platform magnetometers, the light blue was cryosat. Yeah. And green was another one of these platform magnetometers, GRACE, follow on. So you see the kind of coverage you can get both from ground and space during this magnetic storm. So we start to get a quite nice picture. Still, that's at any given instant, it's not a very complete coverage from space. If you look at 1 hour, the satellites are where they are. They're not everywhere. If you look over several days, you've had many orbits. So it takes about 90 minutes for one of these polar orbits, right? So ground stations still have a better coverage globally when you look over a very short time, but there are gaps. And the satellites can help giving a different bit of information there. What's the time here? Yeah, we're doing okay. Are there any questions about satellites? I'm going to talk in a moment about how we use the data. So, yeah.
Because ESD, I think it's from the link curve, right?
Yeah.
So it's a magnetospheric curve.
Yes.
Because you mentioned all our satellites in the atmospheric altitude.
Yeah.
So how can you relate that atmospheric altitude is ionospheric current? So
Well, yeah, so this DST, as we talked about earlier, this is calculated from these 4 ground stations. And so that's DST really is some kind of average of San Juan, Kakioka, Hermanus, and Honolulu. It's not there, but it should. Maybe for some reason the data must not have been there that day.
is there any satellite which is at magnetospheric altitude
Ah,
to
you mean, okay, I understand. Yeah, because these are all, okay, I understand the question. These are all low Earth orbit, so they're down really close to the Earth, not up where the radiation belts are. So the answer is yes. There are other satellites that are more focused on these radiation belt processes. So there's been a number of missions. Cluster was out looking at this Themis, MMS, I think, is this US mission. They typically are making point measurements somewhere in the radiation belts. So they're sampling in situ what's happening in the radiation belts, but they don't get this kind of global picture. Whereas what we can see here is kind of the effect on the near-Earth magnetic field. And actually that's relevant because we're sitting on the Earth. We're not in the radiation belt, so it's actually useful. And for space weather applications, which Alexander might talk about tomorrow, you can get these ground-induced currents. And again, the low Earth orbit satellites are useful for measuring that effect. Yes. More questions? Okay. So now what I'm going to talk about after lunch is how we build global reference, geomagnetic reference models from all this data, ground observatory data and satellite data. And so these geomagnetic reference models, these are basically designed to tell you what the core field is doing. So for that, all these interesting things we saw in the observatory data with daily variations and storms and all of that, in fact, that's a complication we don't want. So we try, when we build these global models, to select the data to avoid these other sources as much as possible. So there's a few typical things that I'll just mention quickly here now that we do. So one is the sampling rate. So we have typically 1 hertz, so 1 second samples from the satellite data. Actually, that's very dense along the orbit, given the altitude they're at. So normally we downsample that to only look at 1 minute samples. That's got sufficient spatial resolution for building these global models at satellite altitude. A second thing we do, and that's really to make the computations not too big. You could use all the data, that wouldn't be a problem, but it would take a lot longer and use a lot more computing resources. So the next important thing is we want to exclude times when the field due to these external current systems, so external to the Earth, magnetosphere and ionosphere, are large. And typically the way we do this is with these indices that I talked about earlier. So we look at, for example, KP or DST, and especially for DST, we often look at the rate of change of DST. So when it's changing fast, then something is happening. KP, that's already a range index. And so what's done is we normally set a threshold value. So this is a little arbitrary, but you set this to say, okay, everything above this threshold I think is too noisy, I don't want it. Right? And then there's some kind of balance. If you're too strict with this threshold, you'll throw too much data away. And if you're too loose with it, you'll let too much disturbed things in. So for example, it could be KP less than 20 would be considered quiet, or a rate of DST change of something like 2 nanoteslas per hour or 3 nanoteslas per hour. So these, these selection criteria, they're fundamentally based on ground observatory data. I can't do that unless I have ground observatory data, right? But once I have that, that's characterizing the disturbance level, and then I can select the quiet data. The second thing that very often is done is that you only use nighttime data, and that's to get away from this daily variation. We saw earlier this daily variation, it's on the day side. Okay, so again, so there typically what you're doing is you're doing a selection based on what's called the solar zenith angle. So the solar zenith angle, so zenith is coming out from the center of the Earth, and then if you have the sun, the angle between the zenith and the sun, this is this solar zenith angle. So when this is 90 degrees, the sun is on the horizon. If it's more than 90 degrees, the sun is below the horizon, and you're in a dark region. So these are typically what we do is then we would select all data satisfying those criteria, and that's what I did here, for example. So you see it's not very dense along the tracks. That's because it's been downsampled, and there's some gaps. That's because there's been some disturbed times, especially in 2024. There was plenty happening with the disturbances. So then you're left with this data set that is suitable for then building these global reference models, which is what we're going to do after lunch. I'd like to leave you with 2 more questions. We had a question about the ground data earlier. I'd like to have you think about a similar question for the satellites. So what are the advantages and challenges of satellite data for studying the present magnetic field? So there are clearly some advantages, there are also some challenges, right? And then you can challenge yourself then. Imagine you had a budget of 20 million euro and you had to give your advice about how to build a high quality global geomagnetic reference field, let's say over the next decades. What would you recommend? How would you recommend this money to be used? So have a think about that given these different types of data, and we can have a discussion later on about that.
Do you have that 20 million euro?
It's in my back pocket. Great. Actually, what time is it now? Yeah.
Yeah, 15 minutes.
Okay, so then I actually have, yes, 2 last slides, because I did want to mention, I've just mentioned the upcoming decades, but I think it's important to know what's happening with this satellite geomagnetism as we look ahead. So this is this picture of the different survey satellites, SWARM and MSS, their altitude as a function of time, going from 2014 up to the present, 2025, and then looking out over the next 5 years. So you can see how the altitude of these satellites has been gradually decaying, and then they've been pushed up at some times using some fuel to do that. And then they've been decaying again, push them up, decaying again. And then you can see how in the past 2 years they've been decaying rather fast. Okay? So the question is, what's going to happen next? All right? And what's important here is the density of the upper atmosphere, and this is very much affected by the solar activity. So what's shown in green here is the observed solar flux. I think this is F10.7, this measurement of the solar flux. So this part is measured solar flux. And so you can see there was a solar minimum here around 2018 to 2020. And then the solar cycle went up again. And when it's been very high in the last year, the satellites have been coming down. So now we're through the solar maximum, and we should be coming down again to the solar minimum. So the hope is that this rapid decrease, you could see it also here, the decrease was rapid, and then it leveled out a bit. So the hope will be that these things will level out, and we hope that the SWARM mission will make it through to the next solar minimum, which will be in 2030. Now, SWARM basically does not have a lot of fuel left, especially on Alpha and Charlie, to push it up again. Basically, it's coming down now. And the question is how fast, and that depends on the sun. Right? MSS was launched more recently. They have more fuel. They can push it up a few more times. So the hope is, at least going forward to 2030, that we will have the SWARM constellation in place and at low altitude, hopefully, to measure with this very high accuracy the internal field. That's what we want. And hopefully we'll have MSS around at the same time, giving this good coverage at low latitudes. And there's also discussion on the Chinese side. So they're talking about 2 more SWARM-like satellites, but in elliptical orbits. So these are in orbits that go between 200 kilometers when they're close to the Earth and out to 1,500 kilometers. So the advantage of these elliptical orbits is that you can stay at a low altitude for a bit longer, but you don't cover the whole globe on each orbit. You only have part of the orbit where you're close to the planet. So they are hopeful about launching this pair of satellites in an elliptical orbit, perhaps on 27, 28 timeframe. But it's not fully confirmed yet, so we have to see about that. But what we do know about is that there will be another ESA mission, something called NanoMagSat. So this is part of what's called the ESA Scout program. So this is a program where they're trying to do things with small satellites, and they don't cost as much as a big mission like SWARM. So SWARM is a big, heavy satellite. It's 9 meters long, including the boom. These are CubeSats. So there's what's called 16 units. So it's about 20 centimeters by 20 centimeters by 40 centimeters. And it has a boom, but a smaller one than SWARM, 3 meters. So there's plan to launch 3 of these. Now this is being approved by ESA. So this is planned to be launched, the first launch by the end of 2027, and trying to have 3 satellites in place by 2028. And they'll be launched into 545 kilometer altitude initially, and they'll have 2 satellites, 60-degree inclination, and 1 going over the poles. And they will have both absolute scalar magnetometer and vector magnetometer. It's in fact a special instrument that can do both of these things simultaneously. So this is very exciting, and this is the immediate future of new missions from the ESA side. So we mentioned this 20 million euro number earlier. So That's actually relevant here. So a mission like this costs on the order of maybe 30 million euro for these 3 satellites. And it's planned for a minimum of 3 years in operation. But so it will be very interesting to see how the quality of these data from these smaller satellites compares to what we have with the bigger satellites, Swarm and MSS. So that's what's coming up on the immediate future. The long-term future, that will be for people like you to decide, I guess. Okay, so that's what I had on satellites. So I think it's getting close to lunch now, right?
Yeah, just in 5 minutes or so.
Yeah. So then the next thing that we were going to do was Ashley has another notebook where you're going to look at some swarm data. And then after, so we'll maybe start that now, or it's up to you. Or we can do it after lunch.
Yeah, I guess we can start it now.
Yeah.
And then it's ready.
Yeah, and then after lunch we'll continue with that, and then we'll come back and talk about how we can use all this data to build these global models of Earth's magnetic field.
So the notebook we're going to look at here is this satellite data selection. So you'll find it down there. And again, you can click on this button to load it, or you can also just find it within the file browser. So this will be an example of accessing some of the swarm data and selecting certain conditions from that data that we will later use for field modeling. Yeah, I can maybe briefly show the swarm spacecraft again. So if you search on the ESA website, you can find this interactive view where you can see a bit more about the instruments. So there's the vector magnetometer and the scalar magnetometer there. And okay, so hopefully you have this notebook open now. Sorry?
Magnetic Earth.
Yeah, I mean, so if just in the Jupyter Hub, actually, if you just navigate to this folder here. Sorry, it's not. Is that readable? It's practical field modeling, and then it's number 2 within there. So here we're going to take the.
I have an error.
Oh,
When I try to refresh part of the import.
oh yeah. Don't worry about that. It still works.
Yeah,
So, yeah.
so maybe I could say, actually, while you're... So it's useful to know about these swarm data files. So they're named SW for swarm. Opera means it's the operational data. That's usually the one you want to use. And then mag, it's magnetic data. And then A, that tells you from its satellite A, satellite alpha. So if it's mag B, am I right? Then it will be Bravo, and then C, it would be Charlie. LR stands for low resolution. That means it's 1 hertz data. That's what's relevant for field modeling. And 1B, that tells you that it's so-called level 1B data. That means it's been calibrated and all these corrections have been applied. So normally you're looking for something like that, but maybe you want to change A to B or C or something like that.
And we have this handbook website here as well that it explains it more. So there's a lot of, it's going slow. Yeah, there are a lot of variables that are stored within this data set, but we're really only looking at this BNEC. So that's the vector measurement in this northeast center frame.
Yeah, so the crucial things always is position, time, and then the magnetic measurements. And if it's NEC, it means that it's already been rotated using the star tracker data into a northeast center frame.
That's the equivalent to X, Y, Z in observatory.
Yeah, it's like X, Y, Z.
Yeah. But there's this BVFM, which is in the frame of the instrument itself.
Yeah.
So that's the data coming from that vector magnetometer. And then there's also F, that's the data coming from the scalar magnetometer. And the scalar measurements are used to calibrate the vector measurements. And then we rotate them into this NEC frame. Then the other variables in there are more about the quality and how the calibration works with the correction for the other fields. But okay. So when we load this there, we can select out one parameter that we're interested in, this BNEC, and we're taking this, we're subsampling it down to 1 minute, so we're only taking every 60th measurement from the data set. And we're taking one month of data. So then you have it there, and then that's the, the vector that we're going to use. Going slow. So this is just going to help you to plot the data. So that's our 1 month of measurements along here. And time, the northeast center components, and then plotted across latitude.
Yeah, so just to orient them a little bit here. So you see there's this high frequency here. This is because it's doing orbits, right? So every 90 minutes it's going through many latitudes, and at different latitudes you're having different field strengths, okay? And then when you plot it as a function of latitude, you see the, for example, the center component. So that's downwards. So in the northern hemisphere, that's positive because the field is coming in the northern hemisphere. It's coming out in the southern hemisphere, so it's negative. So the C component is like minus 40,000 nanoteslas in the southern hemisphere. It's going through 0 on the equator, and then it's going up to positive 40,000 nanoteslas in the northern hemisphere. And it's not if it was a pure dipole field, it would be a single line, this. So the fact that it's spread, that's telling you that you have different things happening at different longitudes. And you can see there's more spread in the southern hemisphere. That's related to this South Atlantic feature.
Why is that?
Pardon?
Why is that? Why is there more spread in the southern hemisphere?
Yeah, so that's a question of why is the dynamo different in this South Atlantic region, and we don't know the full answer to why it's different there. What we can see and I'll talk about this later on. If we go down to the edge of the core, there's a lot of what's called reversed flux in this South Atlantic region, where the field is pointing kind of the opposite direction to what you'd expect. So normally here you would expect the field lines to be coming out in the southern hemisphere. In fact, they go in the southern hemisphere at the core surface. But we have some work to do to get there to understand this. But it's related to this core dynamo process. Yeah. Sorry.
Yeah. So I'm going to switch away from this for a little bit. Yeah, to show the more exciting interface that we have to this data. So there's a bit of a problem going on at the moment. So if you try loading it, sometimes it's not working. If you've seen that before. So if you're seeing this and nothing is loading, sorry. But you can try refreshing after a minute a few times. Hopefully you can get in. But we try to fix it. But yeah, this is looking at 1 day of data here. So these are the orbits that you have along here, showing the intensity of the measurement. And on the surface of the Earth down there, you're seeing the core field. So that's why they're a very similar color there, because most of the signal that you see is from the core. And on the right here, so that's that. Every time you're going around the Earth, that's why this is going up and down as we're sampling the north and the south and moving through the field strength there. This bit on the bottom here, this is what you see if you remove a model of the core field. So these are the variations due to the ionosphere. There's a lot of things you can do in here. So I'm just going to be selective in what I show you. So if we show, yeah, this is what Chris had in some of his slides, showing the vector again. What else? Yeah. So if I turn off the measurements for a moment, you can actually go in and select which model that you want to visualize here. So for example, we can take the crustal field models. So this is showing, oops. Maybe. Oh, yeah, I want to show the. Yeah. Sometimes it takes a little bit of time to load in, but this is the field from the crust. So you have this superposition of all these field sources from the core and the crust, ionosphere, magnetosphere. So you might want to play around with this sometime just to get some intuition about that. But
So this virus interface is very good for both looking at the data directly, but also if you're interested in the models that are derived from the data, which are, of course, continuous, you can also look at these. Yeah.
so the other thing here, I can show the data model residual. So this is the difference between those measurements and the background model. So a lot of the signals you see here, these lines, this is disturbance due to the auroral oval. So that's why you see them clustering around the poles.
Yeah.
So if you select like a larger time range, yeah.
That's nice.
Yeah, and I'm also showing KP along the bottom here, this kind of step-step function here, so you can compare between the quiet times and I think the noisier times. You might see some difference. Yeah.
So they have access to
Yes,
the virus?
yeah, but
Okay.
as I say, sometimes it's not loading, so hopefully you'll find some time to play around with it when it is working again. Yeah. Yeah, and the data's all loaded in pretty quickly, so we can show you some data from, okay, if I, yeah, okay. So this is data from yesterday. Very soon we would have data from today as well. Yeah, but you see here something's going a bit wrong here, and this is actually a problem with the data quality. So we actually have 2 production chains for the data, and this is this fast chain, which is used more for the space weather purposes. It's a bit experimental at the moment, so there's still some issues with the data quality. But if you do a bit more filtering with it and so on, then you can get rid of some of the bad data points. But a couple of days later, we published the normal data, and that's where some of those issues are gone.
Is it the operational data is typically with about 4 or 5 days?
I think it's
delay?
3 or 4, I think.
3 or 4, yeah.
So the next part of the notebook here, we have this data selection procedure. So there's 3 types of selection we're doing here. One is just for data quality, so there are these other variables in here, the flags that indicate that something has gone a bit strange with the instrument, and so you can throw those data away maybe. The second one is this geomagnetic activity, so using this KP and DST indices. So if you're trying to do core field modeling, just throw away that noisy data, right? And the other issue is the sunlight. So if we just choose the night side data, that's where the ionosphere is less disturbed. So it's smaller signal. So the ionosphere, the signal from the ionosphere will be smaller, so we'll be interfering with the
At least in non-polar regions. Yeah.
in non-polar regions. And this is the real challenge, is that around the poles, there's a lot of things happening very quickly. So it's very difficult to select out which data you should use around the poles.
Yeah.
Yeah, so that's what's happening here. So we can add these filters to select which data that we want to retrieve. So now when we plot this data, there are some gaps now because we've thrown some away. So that's all we're doing there, is just throwing away some of the data.
Okay, good afternoon, everyone. So let's get started again. So thanks to Ashley for these very nice notebooks before lunch. So you've now seen both ground data and the swarm satellite data, and you can, if you're interested in using this data, I really encourage you to go away and take advantage of these nice Python tools that you now have access to, so you can use this data for what you're interested in. So what we'll do this afternoon is I'm going to show you at least how I and some others in this room use the data from ground and satellite to build these global geomagnetic reference models. So now it's going to be a little bit more, less on the data measurement side, but more on the modeling side. But before we go into the modeling, I wanted to revisit this question that I left hanging a little bit, which was about the relative advantages and disadvantages of the ground and satellite data. So I wonder if a few of you have been chewing this over a little bit over your lunch as well as with the food. So I'd like to hear so I've written a kind of table here with the ground observatories and the satellite data with advantages for each and disadvantages to each. So maybe we can work through this and have a discussion about it. So first of all, for the ground observatories, what are the advantages that you see there? Yes, please.
It costs less money than sending
Yeah,
satellite.
at least for individual stations, maybe for the whole network. But so individual stations. Let's say less expensive. Yeah, that's true. Any other? Yes, long time series. This is very important if you're interested in these slow changes of the Earth's magnetic field. Having long time series is really crucial. Any others? Any?
People can be covered.
The pole, yeah, no polar gap, yeah, that's in principle true. You can have sites. Maybe it's not so easy to put one on the North Pole if it's in the ocean, but at least sites everywhere on land possible. Any others? Yeah.
Calibrate on ground, but you can't calibrate on satellite.
Yeah, there's got to be something there about the fact that you can really do the calibration accurately. You have full access to doing the calibration. So calibration, I'm going to say you have careful control over the calibration. Yep. Yeah.
Access to the material if there is a problem.
Yeah. So maintenance. Maintenance. Possible. Yeah. So that's, I think, quite a lot of advantages and actually very important ones. And I would say especially long time series and the fact that you're quite sure that you have high quality data, that you really have people with expertise with this data and that have over many years developed careful calibration procedures is really very important. Are there any disadvantages for the ground observatories? Yes, please.
You need a lot of stuff, a lot of people to handle and maintain this.
Yes, so you have to deal with multiple institutes and everything that goes along with that. Even countries. Yeah. The coverage, did you say?
Yeah, you can't put GNSS is in one big ocean.
Yeah. So lack of coverage, or let's say, lack of coverage in the oceans. That's true. Yes.
Surrounding noise like red light.
Yeah. So this is human anthropogenic. Yeah.
Inaccessibility.
Pardon?
Inaccessibility.
Inaccessibility.
Yeah.
In some places, yes.
Yes.
Yeah. Some sites or remote, that's true. There was, pardon? Okay, so the heights, yeah, so that they're mostly on the ground, you mean? Yeah, we can discuss whether that's an advantage or disadvantage. If you're interested in the field on the ground, actually, if you're at the satellite, that's not so good. But yeah, it's okay. Well, yeah, it's on ground. I don't think that's a disadvantage actually, but yeah, limited altitude range. Yeah, any others?
And the temperature conditions, like the climate conditions that can be hot.
Yeah, so provided you're doing this careful control calibration, this temperature conditions you should have corrected for. But in principle, if you're not careful, I agree that could be an issue. Yeah. Okay, should we move on to the satellites? So you can see there's things on both sides here, right? What about with the satellites? What are the advantages with the satellites? Sorry?
We can cover better.
Yeah, global coverage, maybe apart from polar gaps. Yeah, let's just leave it like that. And there was another from the back? Or? Yeah. Yeah?
It's running alone at least. Then we shouldn't need someone to.
Right. So it's, yeah, so
We still need someone there.
so that's automated, I should say that there's a continuous calibration. We could put it like that.
You don't have any noise around.
At least less human noise, but you can have noise from the satellites themselves. So I'm going to put that on both sides. So that could be satellite, body disturbance, but less human disturbance. Related to this continuous calibration, one thing that's interesting is that on ground you have many different instruments, but with the satellite you're really, for swarm it's basically the same instrument on the 3 satellites, so you have some kind of common instrumentation for all the measurements. Common instrumentation at all latitudes. What about some disadvantages of the satellites? Yeah, it's expensive. Especially a mission like Swarm is very expensive.
The life of the satellite.
Yes, that's a very important one. It's a finite lifetime. So for the main satellites we've been talking about, Champ lasted about 10 years. Swarm has now lasted about 10, and we hope maybe for another 5. But these things are not going to be there on the very long term. And then associated with that, you have you need to be careful with inter-satellite cross-calibration issues. Like if one satellite's stopping and the next one starts, you have to make sure there's continuity. That's very different from having single long time series at an observatory.
But then maybe stronger affected by storms, like solar storms.
Yeah, so there's infrastructure, space infrastructure risks. And I would say, at least for the Swarm mission, the thing that we worry about is not so much a solar storm, although that could be bad. It's collisions with all these other satellites that are up there, especially all the Starlink satellites. There's so many of them. Very regularly, there's very close encounters where there's a risk if someone doesn't move, we might collide. This is a big problem. and it's becoming a bigger problem.
And the debris to like all the pieces.
Yeah, if there was a collision, and in some places where there has been collisions, yeah, it's very tricky if you're flying at particular altitudes. Yeah.
And how they are removed, like is there some ground station which is like for controlling, is there something like a controller like
Well,
in a video game?
in ESA, there's a control center in Darmstadt,
Yeah.
and they're telling the satellite what to do. Yeah, but I mean, it's not so obvious with some other satellite constellations if it's semi-automatic or what's going on. So, but there are some protocols in place that try to avoid these things, but still it's not risk-free. Good.
No maintenance possible?
No maintenance, yeah, that's also maintenance. Difficult. Impossible. Yeah. Very good. Okay, so now you can see all 4 quadrants are filled up. And I think in each of these, there's some that are very important. I think for the ground observatories, I would really highlight the long time series and the fact that we have these beautiful, well-calibrated time series. And the fact that, yeah, we can fix them if things go wrong. There's challenges about different institutes and countries and politics and funding. That is a challenge, and the lack of coverage in the oceans, that's a challenge, right? Down here with the satellites, I think the major advantage is we really have the global coverage. And the major challenges, I think, are, well, I think it's the finite lifetime, and that's coupled to the expense. The expense is large because you have to replace it every 10 years, right? Okay, so now we get back to the question. You have 20 million. What do you think? What should we do?
Ground-based.
Ground-based. Yeah. Why?
Because can be maintenance. Its maintenance is easy.
If you have this probability of fail.
Yeah.
Because once the satellite is gone, within 3 years it's burned out. So
Yeah. No, I understand. Yeah. Yeah.
Maybe for 20 million you can have some ground stations and select just one.
Yeah. I like this way of thinking, actually. Right. So, at least from my point of view, the answer is not one or the other. Right. It's about how do we use the resources to make the most of the ground observatory network that we know is crucial for the long term, and we need it for the indices that we need. We can't use the satellite data without already knowing about disturbances. Satellites have some advantages, but I think in order to make the most of the satellites, you also need the ground observatories. So I think the answer would be trying to do something as cheaply as possible with the satellites, and then also investing to continue the long-term viability of the ground observatory network. Yeah. You have a comment?
But Starlink has a lot of, satellites and money.
Yeah.
Did they think about like doing something with science? I don't know what they are. If we could maybe put some stuff in some magnetometer on the satellites.
Yeah, so I talked to you about these platform magnetometers earlier, where these are satellites that weren't specifically designed to measure the magnetic field. So in fact, there has been some discussion. These things, they have magnetometers on, not very good magnetometers. And there's a lot of noise from the spacecraft. There's no boom. But maybe if you wanted to try to characterize with, let's say, not very accurate measurements, maybe for space weather purposes, when there are large storms or something going on, could be useful. But as I understood, it's, at least at the moment, there's not much collaboration going on. So but I know there are other constellations that perhaps are more open to these things. But at least we as scientists are certainly thinking about, is there some angle there? Yeah. But you need the industry to be willing to play with you. Yeah.
But do you think there will be a limitation in the future on sending satellites because of all these satellites sent by Starlink? Because at the end, they are not going to be able to work each other.
Certainly getting more complicated. That's all I can say. Yeah. At the moment, I think it's not. yeah, it's fine, it's possible, but if you get 10 times more, it really, there would at least need to be some well-designed systems to avoid these collisions. And I think nowadays there is more restrictions. You can't launch satellites into whatever orbit you want. They have to deorbit by a certain time. That wasn't the case in the early days of space. Yeah. Yeah, last question, and maybe then I know I like the discussion, but we should need to move on.
Is there any thoughts about the construction of ground observatories on the ocean?
Yeah, so actually, of course, we also have been chatting about this this morning. So yes, because of course, if you could fill the gap like the seismologists try and do, it would be great. So the Japanese, there's some Japanese colleagues here, they have been working on doing this in some places. My understanding is it's very challenging logistics-wise. First of all, it's a bit different from seismology. You're in a conducting medium, which is the water of the ocean. And it's not so easy to orient things. To do absolute measurements is not so easy. So maybe with a variometer, you could get something. But then there's also a kind of skin effect because you're in the ocean, that the very fast variations will get filtered out if you're 4 kilometers down. So at the moment, the favored solution there is to go for islands. And I think BGS have some quite interesting ideas about so one of the places where there's at the moment the biggest gap, if you look at where there's a place where you're furthest as possible away from all other stations is in the Pacific. And there's a place called Pitcairn Island there that I know Kieran could probably say more about this. But there's a plan, at least it's under discussion, it would be great if something could be put there. And that would, again, try to optimize this global coverage. So that definitely is what I'm saying, like think about how to smartly invest things. So, yeah.
I mean, one of the other issues with an ocean bottom magnetometer is how do you get the data off it? I mean, that will sink to the bottom of the ocean for a year, and you'll get your data back. So that's a disadvantage.
Okay, great. Well, keep that complementarity in your heads when you hear these discussions next week at the conferences. Okay, so now I'd like to move on to how we try to build global models of the Earth's magnetic field. So what I'd like to do is to begin with the physical framework. And when you're working with magnetic fields, the answer for how you describe them is it's almost always, the answer is Maxwell's equations, if you're interested in physics. So in terms of Maxwell's equations, the things describing the magnetic field are we have that the divergence of B is 0, that you have no magnetic monopoles, and then we have that we have the Ampere law that tells us that the curl of J is equal to, the curl of B is equal to mu naught J, plus then we have this so-called displacement current. Term. So it involves the time change of the electric field, the electrical currents, and then that is telling us about the magnetic field, right? So we all know this from Maxwell's equations. Now, the way we go forward trying to build global magnetic field models is we're going to make some quite dramatic assumptions in this second equation, right? So what we're going to say is that in this region where we're mostly interested in things, let's say from outside the core, where we know there are strong electrical currents, but let's say in the mantle, which is the first approximation at least approximately an insulator. And then if we're in the atmosphere, then we have that the electrical current density J is generally small, okay? So we're going to say that J is going to 0. And we're going to look at very slow changes in the magnetic field, right? So this term here, this constant, that's like 1 over the speed of light squared. That's a small number. So this only becomes important if you have very fast changes of the electric field, right? So when in geomagnetism, often we're looking at timescales changes happening on timescales of, let's say, minutes, hours, days, years, centuries. For this thing to be important, you really need to be looking at things like much faster than 1 second. So for some space physics, this is important. But for this core field that we're interested in here, we'll also say that that one is going towards 0. Okay? So that means that the curl of B is, we're going to say to a first approximation, the curl of B is 0. Right? Now, when the curl of a vector field is 0, turns out if we write B as equal to the gradient of a scalar potential, let's call it V, and we'll put in a minus sign here, that's just a convention. Now if I write the magnetic field like that, if I then take the curl of that, I take the curl of a gradient, curl of gradient is 0 always, right? So that means if I write the magnetic field like this, I guarantee that this statement above is true. That's built in. And this thing, V, we call the magnetic scalar potential. So this is nice because now we have one scalar field everywhere. And if I tell you what that is, you can then calculate all the 3 components of the vector magnetic field just by taking gradients. Okay, so that's a really important simplification if these assumptions I've told you are correct. Okay, so this is when we talk about potential field modeling, we're representing B in terms of this scalar potential. Okay, and then when we also have that the divergence of B is 0, so if we then take the divergence of this, then on the left-hand side, the divergence of B is 0, and then the right-hand side, we have the divergence of a gradient. That is the Laplace operator. Okay, so what that tells us is that this scalar potential must satisfy Laplace's equation. So now, if we want to build models that are compatible with that physics, we need to search for solutions that we can write in terms of solutions to the Laplace equation. Right? This slide just said what I said on the board, more or less. Now, because we're dealing with planets and the Earth, that's to first approximation, a sphere. So we should work in spherical coordinates, spherical polar coordinates. So that means radius, theta is the co-latitude, not the latitude, but co-latitude, so measured from the North Pole, increasing as you go southwards, theta. And then I'm going to call longitude lambda. Sometimes people use phi for that. Okay? So r theta lambda for this spherical polar coordinates. So now what we should do is get this Laplace operator in spherical polar coordinates. And we know it. You can write it down, and that's what it is. So it involves a term in radial derivatives, a term, there's a 1 over r squared sine theta, but then it's some theta derivatives, so latitudinal derivatives, and then a term that involves longitude derivatives, right? And there's second derivatives here, because it's a Laplace, because we had divergence of the gradient. So you then need to solve that. We could do it, but it would take us some time. So I'm just going to tell you the solution. Maybe you've seen it before. It's a very classical piece of classical physics. So this can be solved using something called the method of separation of variables. So you let the scalar potential V, you assume you can write it as a product of a term that depends only on the radial, only has a radial dependence, a term that only has a colatitude dependence, and a term that only has a longitude dependence. And when you separate these in, when you substitute this in, you'll find that this big equation separates out into 3 ordinary differential equations, and you can solve each of those. And the solution we can write in the following form. So later on, I'm going to come back to talk about external sources, right? In principle, there are 2 solutions to this equation. One representing currents that are below you, we call those internal, and one which are outside. These are external currents. So remember, in the region we're operating, the current density is 0, but there can be sources below us or above us. For these internal sources, the solution looks like this. So it has a double sum, and so there are 2 indexes involved here, n, which we call the spherical harmonic degree, and m, which we call the spherical harmonic order. And if we look at where these are integers, right? And if we see how these appear, so a here is the radius of the Earth's surface. That's a reference radius that we use. And then we have, in this term, we have a radial dependence. It goes like a, Earth's surface radius, divided by r, and that's raised to the power of n plus 1. So for example, if n is 1, we call that the dipole solution. Then this goes like a over r, n is 1, so it's a over r squared. The potential goes like a over r squared. Right? If you took another derivative to get the magnetic field, it would go like a over r cubed for the dipole. Right? So that's the radial dependence. It's a power dependence. And what you can see here is that as the radius gets smaller, so as r becomes smaller than a, that term becomes bigger than 1. As r gets very large, so if r was 10 times a, 10 times the Earth's radius, that would be 1 over 10. So that's saying as you go far away, this term gets small. That's normal. If for internal sources, as you go further away, it decreases. The next part here, so this is a cosine and sine of lambda. So sine and cosine in longitude. This is in fact like a Fourier series in longitude. And that makes sense. Fourier series is all about how you represent signals that are periodic. And on the sphere, when you go around in longitude, you're periodic. When you come back through 2 pi or 360 degrees, you have to get the same thing again. So any signal dependence on longitude, we can represent it as this essentially Fourier series in longitude, where we have m is telling us how many waves we have in longitude. Okay, so that's the longitude dependence. The third bit is the colatitude dependence. So this is just a symbol right now, PMN cosine theta. These things are polynomials in cosine theta. They're called the associated Legendre functions. We'll look at them in a moment. Essentially, this is more complicated than what's happening in longitude because we have a north and south pole. It's not periodic in that direction. What's happening in the North Pole and the South Pole can be different. So we need a different type of description than a Fourier series. So it's done in terms of these associated Legendre functions. So the combination of the longitude dependence and this colatitude dependence, which is either cosine m lambda PMN cosine theta or sine m lambda PMN cosine theta, these things are called spherical harmonics. And so this solution is built essentially of a sum of these spherical harmonics. And these coefficients g and h, they tell you how much of each spherical harmonic you have. So essentially these spherical harmonics are the equivalent of the sines and cosines that you have a one-dimensional problem to a sphere. So in the same way you can decompose any signal in sines and cosines, you can decompose any signal in the sphere in spherical harmonics. So the bit that's new, you all know about Fourier series, but the bit that's maybe a bit new is this associated Legendre function. So here's pictures of what these things look like as a function of the order n and the degree m. So for m equal to 0, n equal to 0, when both these degree and order are 0, this is just a constant. Actually, that's not allowed for a magnetic field because there's no magnetic monopole. This would correspond to a magnetic monopole solution. If you had a single magnetic monopole at the center of the planet, it would have a constant value everywhere on the sphere. That's not allowed. So the first one that we have that's physically possible is this one. N is equal to 1, m is equal to 0. And that involves, so it's positive 1 in one hemisphere, it goes through 0. Oops. EZ. Thank you. And then it goes to -1 in the southern hemisphere. And if we stick with m equal to 0 for now, that means things are the same at all longitudes. Then you'll see that as n increases, we get more crossings of the 0 line. So for n equal to 1, we had 1 0 crossing. For n is equal to 2, we have 2 0 crossings. N equal to 3, we have 3 0 crossings, and so on. So as you go up in this index n, spherical harmonic degree, you get more complicated structure in latitude. So on this axis, this is the co-latitude, going from the North Pole to the equator to the South Pole. Now, it's a little bit more complicated than that because you can also have different orders. That means different longitude dependence. So as m goes up, then it's actually the combination of n and m that matters. So the number of 0 crossings you have actually depends on n minus m. So you have n minus m 0 crossings. Yeah. So here, for example, n is 3, m is 1, 3 minus 1 is 2. I have 1, 2, 0 crossings, not including the poles. Yeah, down here, n is 5, m is 2. 5 minus 2 is 3. I have 1, 2, 3, 0 crossings. So if you want to know how many 0 crossings you have for a certain spherical harmonic, it's n minus m. That is the thing to bear in mind. So now I'm putting together the latitude dependence and the longitude dependence. And so these are now pictures of these so-called spherical harmonics, these building blocks in the sphere. So this is the dipole, quadrupole, octopole, and so on. For m is equal to 0, they're the same at all longitude. For m is equal to 1, you have 1 wave in longitude. M is equal to 2, you have 2, and so on. So you can see these patterns and how they get built up.
What is the n and n1, m1? Because it's not a dipole, or it is a dipole. n1, m1.
M1, yeah, it's a dipole, but it's oriented in the horizontal plane. So it's where the dipole is on the sphere. So because there's 3 axes involved, yeah. So you have that one, that's called the axial dipole, and then you have this one, and you can have one of these associated with the cosine m lambda, and then you have one associated with sine m lambda, right? So there's 3 of them in total. Yep. And I'm not going to go into the details here, but you have to be careful about how you normalize these things. These are functions on the sphere, and you have to decide when you integrate them over a sphere, how you're going to normalize them. And in geomagnetism, we do something called Schmidt quasi-normalization, and this is the way the Legendre the associated Legendre functions are normalized in that case. So if you talk to geodynamicists or seismologists, they also use spherical harmonics, but they might use a different normalization. So you need to be careful. Or in quantum mechanics, they also use spherical harmonics, but again, it's a different normalization. So there's certain classes of these spherical harmonics. Ones which don't depend on longitude we call zonal, so they're the same at all longitudes. When n is equal to m, then there is no zero crossing, so it gets maximum on the equator. That's called a sectoral harmonic. And then anything else, which is some more complicated pattern, that's usually called tesseral, right? So that's just some terminology. And there's a table here. I'm not going to go through it, but you can see how the different spherical harmonics get built up. So for a certain n and m, here you see the longitude dependence. And this is what the associated Legendre function looks like as a function of theta. So for example, for n is equal to 1, this Pmn is cosine theta, right? This is this dipole dependence. For n is equal to 2, m is equal to 0, it's cosine squared theta. So we know these functions, you can look them up in tables, and there are what we call recurrence relations for generating these in sequences. Okay, so this is a whole machinery, but we know how to do it. Okay, so now we have a quiz about what spherical harmonic we have. Right, so here is some spherical harmonics. It's as a function of colatitude and longitude. So North Pole, equator, South Pole, longitude, right? And we have some variation in this, on this spherical surface. So what spherical harmonic could this one be? What would n and m be in that case? 1? Yeah. Yes, so I think you're saying n is equal to 1, m is equal to 0. Yes, that's correct. Because there's no dependence on longitude, it has to be m is equal to 0. M is always the easy one, right? You just count how many waves do you have in longitude. And then n, okay, that's about how many zero crossings you have. So if it's n minus m zero crossings, m is 0. I can see there's 1 zero crossing here. So n must be 1. Yeah, it's also the dipole. That's this basic axial dipole structure, right? What about this one? So it's 6, yes. So m is equal to 6 for this one. Yeah. The last one is kind of half covered, so it's half on and half off. But there's 1, 2, 3, 4, 5, 6 maximum. 6 waves. So m is equal to 6, correct? And what would n be here? Yeah. How many zero crossings do you have? So it's easy. I find it easiest if you look at it in the bottom plane here. Somehow the 3D thing is hard to see, but if you look at it down here, you see it's got a maximum on the equator. And in fact, there's no zero crossings there. It's 0 at the poles, but it's not going through 0 elsewhere. So n minus m is 0 in that one. Well, you don't count the poles when you're counting these zero crossings, but it goes from 0 to a maximum to 0. It's crossing 0 as a function of longitude, I agree. But if you look as a function of colatitude, it's not crossing 0.
Yeah, okay, I got it.
So in fact, it's one of these ones.
We are not really there.
So there's in fact no zero crossings, so that means n has to be equal to m. N minus m is 0. M is 6, so n is also 6. So that is n is equal to 6, m is equal to 6. I'm not going to do the other two.
We are too much.
You get the, if it was a full semester, we'd do everything. Okay. There's a very nice web page at GFZ where if you click, so the URLs that are in these PDFs, you could click on them and they take you there. And there's a kind of interactive web tool where you can put in the degree and order and have a look at these things. It's kind of fun. Okay, how are we doing for time? I'm going a bit slowly, I fear. Well, when do you want to start the next practical or a break? Should I keep going for a bit?
Yeah, I think we can keep going.
Are you ready to keep going? Okay, so now we've set up some of the machinery of this spherical harmonics, but now we need to come back to the geomagnetic setup and think about how we work here. So here, the basic scenario we've got, you have some currents somewhere in the interior of the Earth, and you have some currents somewhere out there, and then in this region in the middle, you're assuming that J is equal to 0. The current density is 0. And that means that you have minus grad V is B, and that the Laplacian is 0. Okay, so the full solution to this Laplace equation, and it's a bit small to fit on the slide, but I hope you can see it. So now, in fact, in addition to this internal sources that we talked about first, there's another term that involves the external sources. And it's exactly the same, except it has a different radial dependence. So now, before for the internal sources, it was A divided by the radius. So that meant as you go to big radius, it got smaller. Here, it's R divided by A. So now as you go out to bigger radius, this term gets bigger. So the different radial dependence, so internal and external sources, you can distinguish them. And this is beautiful, by the way. This was Gauss. This is Gauss, right? He said, if you solve Laplace's equation, then you can really distinguish these internal and external sources. Okay? But they have the same kind of Fourier series in longitude and the same associated Legendre function, same spherical harmonics, but different radial dependence. So we now have also we need more coefficients to describe the model. So we have coefficients for the spherical harmonics for the internal sources. We call these GMN, so G, M order, N degree. HMN is associated with sine M lambda of the internal sources. And then we have for the external sources, Q and S that are associated with the cosine and sine. So in geomagnetism, it's conventional to usually work with, these are real spherical harmonics. So it's also possible to express that sines and cosines in terms of a complex number, complex exponential, in which case you can write things a bit more compactly, but it's also an extra layer of abstraction. So we normally just use the real spherical harmonics with sines and cosines. So now we have, these, if I give you all these GMNs, HMNs, QMNs, and SMNs, I give you the model of Earth's magnetic field. And from that, you can compute the potential at any place you like. And if you take its derivatives, you can compute the Z component, the downward component, the eastward, the northward component, or the X is the northward component and Y is the eastward component. So this involves just taking the right derivative in spherical geometry. So for the radial field, it's the radial derivative. Looks like it could be complicated, but it's actually very easy because the radial dependence is just a power. So if I differentiate that with respect to radius, I get a factor of n plus 1. And the minus sign is coming as well here. And this power goes up to n plus 2. And it's a different dependence on n when you take the derivative for the external field, because it's r to the n. When I differentiate that with respect to r, I get a factor n. And then similarly for the theta derivative, you have a 1 over r, and then you need to take the theta derivatives of your associated Legendre functions. They're all polynomials in cosine theta. You can do it. For the eastward component, it's a derivative with respect to longitude, but that's just taking a derivative of sine and cosine. Again, you know how to do that, and you're going to get some, yeah. Yes, okay, so then an example of how you can use this. So we can simplify a little bit. If we work at Earth's surface, that's also a place we're interested, then the radius is equal to a, then all this r over a things, it's 1, right? So this then becomes the expression for x, y, and z, where now I've written these things a, b, alpha, and beta, where a is a combination of g and q, and b is a combination of h and s. So the a and b, which you get from the x and y components, they involve a sum of the internal and external coefficients. The alpha and beta, which you get from the z component, they involve differences in the external and internal coefficients. And in fact, so these are a set of simultaneous equations, and you can solve those, rearranging them to write G, H, Q, and S, which is what you're actually interested in terms of this A's and alphas and B's and betas, right? So the reason I'm talking to you about this is if you measure either X or Y and Z, then you can determine both the internal and the external coefficients. So if you measure the full vector field, you're going to be able to separate internal and external sources, right? Because you'll first determine these A's and B's and alphas and betas, and then from those, you can rearrange them to get the internal and external coefficients out. So that's why it's part of the reason it's very important to measure the full vector field. If you want to separate internal and external sources, you can't do that if you only measure intensity alone.
Sorry, Grace.
Yeah.
Yeah, I want to ask, is it possible to model the magnetic field on the Cartesian coordinate at least to some level of approximation?
Yeah, so if you're interested in just some region, like let's say, a model of the magnetic field in Portugal, then to first approximation, you can assume things are flat, and then you can do it in Cartesian coordinates. But if you want a global model,
because I asked you because in my model that I'm using to study
Yeah.
plasma physics,
yeah.
so I needed to do it in Cartesian.
Yeah, okay.
So I needed to be sure what I'm doing.
Well, okay,
Of course, it's just a localized, like earthquake epicenter.
yeah. I mean, formally speaking, I think the physics shouldn't depend on what coordinate system you choose, right? So that means in practice, if it's simpler for you to code it in Cartesian, you could do that. But there might be some parts that are very complicated and involve a lot more derivatives. The analytic solutions are much simpler and cleaner if you work in spherical coordinates.
Okay.
Yeah. Yes. Okay, so now we've talked quite a lot about how we represent the magnetic field in terms of the gradients of a potential and in terms of a spherical harmonic expansion. So in fact, this is what is called a linear forward problem. So here, if I give you the model coefficients, the GMNs and HMNs, so you'll have a whole list of these, one for each of these spherical harmonic patterns. I give those to you. You can then fill them into this expansion and you can calculate the component of the magnetic field you're interested in at some location, right? And then let's say you're interested in another location, so another position and maybe another field component. You can also write down the spherical harmonic expansion for that. Again, if it's a vector field component, it will depend in a linear way on these coefficients, the GMN and the HMN. So in fact, it's possible to, if we want to make predictions with a magnetic field model, we can write things in this form. So some prediction of the magnetic field, some data, D, we can write that as a big vector, and then we can calculate that from the model coefficients if we know this matrix G. So this matrix G we call usually the design or sometimes the kernel matrix of this linear forward problem. And so the elements of this G matrix are in fact just the different terms of this spherical harmonic expansion. So this G matrix, it's, so we have D is equal to GM. So we have a big list of measurements of the field, like it could be BR at some location. And then I have my list of model coefficients. So that would be my Gauss coefficients, for example, starting with the axial dipole, G10, G11, H11, and then G02. So I'm now just listing all these coefficients. And then I have a matrix that's connecting these things. And the rows of this matrix correspond to data. So this thing, it's a matrix that's of size number of data. It's got as many rows as we have data points that we want to make predictions of. And it has as many columns as we have model parameters. So this first entry here, it corresponds to the first data point that I want to predict, and it corresponds to the first model coefficient, G10. So I need to think about, in my spherical harmonic expansion, what bit corresponds for BR to G10. Okay, G10, so I'm going to have A over R, N is 1, so it's going to be A over R cubed. N is 1, so it's going to be 2A over R cubed. And cosine M lambda, M would be 0. So cosine M lambda, that's 1. So I just have GMN there. HMN, well, sine M is 0. That term's not present. And for the axial dipole, this is cosine theta. So this first entry here would be 2A over R cubed cosine theta. And then I just need to work through all the other terms in my expansion corresponding to the higher spherical harmonics. And then I go to the next data point, which will be at a different position and could be a different field component. Okay, but so once I have this G matrix built from the spherical harmonics, I can make predictions for the field. So that's what's shown here in the next slide. It's even a simpler situation. If we're at the Earth's surface, R is equal to A, then for BR, it's just 2 cosine theta that corresponds to G11. For G10, for G11, it would be 2 cosine lambda because m is 1, and then sine theta is the p11. So if you wanted, you could do this by hand. You know the formula, but it would be very, very slow, right? So in practice, we have some Python packages that we can use to compute this matrix, right? And so there's a Python package called Chaos Magpie that Clemens Kloss, one of my colleagues at DTU, has written. And that has a function inside it called design Gauss. So it gives the design matrix for the Gauss coefficients if you give it some locations of interest. So if you give it a set of locations of your data, a list of radius, latitude, longitude, it's going to return this G matrix. So now we know how to go from model to predictions of the magnetic field. You do it by one of these G matrices. And I'm almost done. We're going to have a break soon. But the last bit here, and this is actually not so difficult now, because so far I've talked about, okay, if I give you some coefficients, how do you compute what the magnetic field is? Okay, but it's not that we want to do. Normally we want to build a model from the data. So that we call the inverse problem. We want to get the model coefficients given some observations, satellite data, ground data, right? So that's what they call an inverse problem, right? Going from data to model. So the simplest approach to that is to minimize, you find the solution for the model parameters which minimizes the sum of the squares of the difference between the data and the model predictions. So now D here, I mean D observed data, and then from that I subtract GM, that's my model prediction, right? So that's the difference between the observation and the model prediction. And so that is the sum of the squares of the difference between the data and the model prediction. So if I minimize that thing, I'm going to find the solution for the model parameters that fit the data best in this least squares sense. Okay?
How do you get this model prediction?
This GM,
Yeah.
how you get it?
Yeah, I mean, because you need somehow model before, right?
Well, in principle, yes, but I'm just going to say that's something I want to minimize, and then I'm going to make a derivation that then tells me what m minimizes that quantity. So it's an optimization problem. As long as I know the data and I know GM, I don't actually have to check this each time. I'm just computing how to minimize that. So what I do, I have to differentiate that thing with respect to m. M is the thing I can change, right? So that's a quadratic function of m. So I differentiate this with respect to m, and well, yeah, we can write this out in full. So that's a product. So it's going to be d transpose d minus gm transpose. Okay, I think I don't want to do it in real time, but it's an exercise. Expand this out and then differentiate it with respect to m, and then you set that to 0 because that's where the minimum is, and you'll find that this is the solution. I can also schematically say to you that this makes sense. If d is equal to gm, and you want to get m, you might think, oh, well, I can just do m is g to the minus 1d. But I can't do that because that matrix is not square. But if I multiply both sides by g transpose, I can say that that is true. And then if I multiply both sides by g transpose to the minus 1, I will get g transpose g to the minus 1 g transpose d is equal to m. which is also what you get if you do this proper least squares derivation. So this, I think some of you will have seen before. This is the least square solution, right, for model fitting. So if you have a linear model, this is how you derive the model coefficients from the data. And you can do that in NumPy, for example, using a linear solve operation. There are some extra steps you can do to make this a bit more complete. If you know that your data have different errors, different weights associated with them, some data are more accurate than others, you might want to include a weight matrix here. And if you include variable errors on your data, then this is the so-called weighted least squares solution, where W is a diagonal matrix with weights. So each element in W gives a weight for the data. It can also be that this least squares solution is unstable in some situations. And in this case, you might not always get a good answer from the least squares solution. And in that case, you might want to add something else to the thing you're minimizing, some measure of the kind of complexity of the model. So this you can measure, you can do by adding, this is a quadratic term, this is a quadratic function of the model parameters. So this could be something like the radial field integrated over a spherical surface, for example. And alpha squared is some positive constant. And in that case, when you add this extra so-called regularization term, you modify the thing that you're inverting you're adding this so-called regularization matrix. So this is maybe a bit more advanced, but for those of you who are into inverse problems, you'll know that sometimes you have to stabilize them by adding a regularization term. Okay, so I think now we've got through, so the basic story here is we know how to make predictions using our spherical harmonics. We need to build this G matrix, right? And then we're going to minimize this cost function, and then that gives us a formula for computing from the data, the observed data, and this G matrix that connects the model parameters and the data. So once we have G, then this is easy. I can always compute transpose of G, and I can solve that linear system. It's one line in Python. So all the work is getting the G matrix, which is all your spherical harmonics. So last thing, and then I think I at least need a break. So what can you do once you've built all these models? So now once I have my spherical harmonic model, I can then predict the field at any altitude, any longitude, any latitude. I just fill in those positions into my spherical harmonic expansion. So this is an example of a field model derived from satellite and ground data at the Earth's surface in 2010. So that's nice. It's some kind of compressed version of all the information we had in the data, assuming that these things about the physics, these assumptions we made. Now I have, just from this list of spherical harmonics, I can compute the field at any location I want. And what's also interesting is I can also do it at any altitude I want, provided this is still true. And for those of us who study the core field, in fact, I really want to know what's happening down in the core mantle boundary. And to do that, I need to go down in radius. And it turns out, if we still can assume that electrical currents are not so large, at least on long time scales of the core field in the mantle, then what we can do is just apply the spherical harmonic expansion, now not with the radius at the Earth's surface, but the radius of the core mantle boundary. Okay, so can I just show the movie and then I'll come back here? So what I'd like to show you is what happens when you evaluate this kind of model as you go down in radius. So if you start off at the Earth's surface, things look rather featureless. It's predominantly dipolar. And now as we go down through the mantle, as we get closer to the source, what happens is these higher spherical harmonics become more and more important. So now we start to see lots of the non-dipole structure of the magnetic field. So if we really want to answer some of the questions you were asking me this morning about what's happening in the South Atlantic and so on, we need to look not at the field at the Earth's surface, but we need to look at it down at the core mantle boundary. And to do that, we have the technology to do that, provided these assumptions are valid. And so this is this field at the core mantle boundary now unwrapped. So you see it's still approximately dipolar, but you have these concentrations of the field. And one thing you should, I hope, see is that there's something weird happening in the South Atlantic here. You have blue in the orange hemisphere. That means when most of the field lines are coming radially outwards, orange, there's some other bits where it's going the opposite way. So this is fundamentally the reason why the field intensity is weak in the South Atlantic. That doesn't tell you where this comes from, but that's what it looks like down there. And when we study the core field, what we are very interested in is the time changes of these. These are concentrations of the magnetic field produced by the dynamo process in the core. And some of them, for example, these low latitude features are moving westwards. And these high latitude features under Canada and Siberia and Australia, these are very important for the largely dipolar field we see at the surface. So once you've got your spherical harmonic model, there's many things you can do with it. Now, Kieran, you had a question.
I was going to point out that basically just created a model of 95 numbers.
Yeah.
Yeah, so it's extremely compact.
It's super compact. Yeah. So that could have been derived from, okay, it's at a single time, but it could have been derived from many thousands, hundreds of thousands maybe of data. So it's an extremely efficient way of compressing the data that we've got, and it's extremely efficient because we've built in the physics, right? It was the physics that allowed us to go from a vector field to a scalar field, and then from a scalar field that we could express in terms of these spherical harmonic patterns that satisfy divergence of B is equal to 0 and grad B is equal to grad V. So yeah, I agree. That's a very nice feature of it. Yeah.
But I heard about a model that is spherical cap harmonics.
Yes.
So it's like it's kind of global, but more Europe-centered in a part of the world, or how? What is the main difference?
Yeah. So that's it's actually very closely related to this, except these Legendre functions in colatitude, they don't extend globally. They extend only for a small cap. So you could imagine just take the North Pole and then some maybe 30 degrees around the North Pole, and then you could rotate that to any position you want. And in fact, that's the way people are building very high resolution local regional models of the crustal field. Erwan Thibault in France is doing that, for example. And people do it also in space physics for studying like polar current systems, for example. So yes, if you want to do things regionally, there are ways you can modify these global spherical harmonics to do that. Yeah?
Is people in mining like measuring magnetic fields so you can have somehow an idea of the magnetic field inside the Earth?
Yeah, so people have measured it going down in mines. I think the deepest hole is what, 13 kilometers is it in? It's very shallow. So here, this is 3,000 kilometers down. So no one's making direct measurements down there. But people do make measurements in mines because they're interested in navigating down there. What can be a problem is local magnetized rocks. So you need a much more detailed model in that situation of the local anomalies. Yeah. But certainly it's an interest for applications, yeah. Okay, so should we break?
I think we still have 15 minutes to break. I don't know if
Okay, I can do one last bit, and then I think we should take a break. So there's one other very useful diagnostic with these spherical harmonic models I wanted to tell you about. And that's something called the spherical harmonic power spectrum. So this is a way of calculating how much power you have, so power in the sense of magnetic field squared, as a function of spherical harmonic degree. So essentially what you do is you take all your spherical harmonic coefficients for the internal field, G's and H's, and for a given degree, n, you sum up all the m's, so all the different longitude dependencies. So you square the coefficients and add them up for a certain m, and then depending on what radius you're interested in, you have a radial factor, and then you have an n+1 that comes from the fact that you're looking at the vector field squared. So this thing is once you have these spherical harmonic coefficients, it's very easy to compute that. That's one line, and that can tell you how the power in the magnetic field is distributed as a function of spherical harmonic degree. And spherical harmonic degree is like inverse, it's a wave number, it's like 1 over a wavelength. So when the spherical harmonic degree is small, you have very large scale, like the dipole, and then as you increase this, you're going to smaller and smaller patterns in the sphere, right? So this was a plot I showed you this morning, but now you understand a bit more about what this spherical harmonic degree is. And the dots here are from a model of the internal field. And so what you see is for the Earth, as we go up in spherical harmonic degree, the amount of power is dropping off, in fact, very rapidly, up until about spherical harmonic degree 13. And then after that, it's not quite flat, but approximately flat, maybe slightly decreasing. And when you have this very steep slope here, this steep slope is telling you that the source is far away. It's telling you, if you have a source that's far away, if you think about this radial dependence, this r over a to the power of n+1 or n+2, if you have a source that's far away, it nearly always just looks like a dipole. As you come closer to it, you see more and more. So the fact this is so steep, this is telling you source that's somewhere deep in the Earth. This bit that's flat, that's what you would expect if you were sitting right on top of the source. So this is in fact the core field, and this is the magnetized crust, lithosphere, upper mantle part of the Earth's magnetic field. And so that's telling you, when you see a spectrum that's shaped like that, it's telling you something about the interior of the planet and where the sources of the magnetic field are. You're seeing that most of the power is coming from the deep part of the planet, the core, and at small wavelength, we're getting sources from the crust. So what's interesting then is that you can go and make magnetic measurements in other planets and see how their power spectra look like. So blue is, again, the Earth, right? Purple here is Jupiter. So we have that up to about spherical harmonic degree 20 now with the Juno mission. And there we have a steep decrease, maybe not as steep as for the Earth. So that means probably the source in Jupiter is shallower. It's probably not in the core of the planet, but there's none of this flat bit, right? So this is telling you about where the dynamo is in Jupiter. It's probably in a metallic hydrogen layer at about 8/10 of the way out of the planet. Red is Mars. So what's really different between the Earth and the Mars is you don't have this steep bit at low degree. That's because you have no core dynamo in Mars. So you just have this bit where it's more or less flat. This is the magnetized rocks at the surface. Black is the moon. It looks like Mars, except it's weaker. Mars is more iron, it's red, so it's got stronger magnetization. The other lines here, Saturn is the olive colors. It's also quite steep, although it's some scatter. And then Mercury, we don't have a lot of data, and Uranus and Neptune, we don't have a lot of data. But so by building these spherical harmonic models, we can learn about the structure of the planets, and especially by looking at these power spectra. And now I definitely would like to take a break, and you do too. So.
Okay, so in this notebook, we're going to actually make a model using quite a crude approach, but it'll be quick, and hopefully you'll see it's not too mysterious. Yeah, and it's just kind of a starting point to see how you might start to build a more serious model. So yeah, as Chris mentioned in the slides before, there's this Chaos Magpie library that we'll use to create the design matrix. Yeah. So again, if you just so is this making a main field model, and you can launch it just like the other ones. So if you start reading through it and execute each cell as you go. So this is the data set that we're going to use. It's downloaded from BGS, but it's just an annual means data set. So it's just we're just taking one value from each observatory for each year, and we just take out 1 year from that. So we'll only have 100 or so numbers in there, one from each observatory that we're using. So there it is there. So these are all the observatory codes. So we have 164 observatories in there. And down here you have the components that we're going to use, the Z, the X, and the Y there. So don't worry about all that red text. It's complaining, but it's still working. So you can just view the data there, so you can have a look at each one, see what value is there. We're just showing this vertical component. Yeah. So just like in the slides earlier, we're going to create this design matrix G and do the inversion for it. So yeah, this is where we use the function from the Chaos Magpie just to create that design matrix, and that's separated into each of the components, and we just put it together here. So it can be as simple as that to create a model, so that M out of it at the end are our Gauss coefficients. So if you look at the first one there, that's the magnitude of the dipole. This there.
Yeah, so it's minus 30,000 nanotests approximately.
So I'll leave you to go through that yourself and get up to this point.
So you've chosen a maximum truncation degree of 6 there?
Yeah. Yes, so yeah.
So when you call the design Gauss, you have to tell the maximum spherical harmonic degree you want to go up to. Yeah.
So this is the maximum spherical harmonic degree. N.
Do you have the formula up above there?
Is this N that we were talking about?
Yeah.
Yes, yeah,
But
sorry.
so there's a sum, there's this double sum. Yeah. So the first sum is over the degree, which is telling you about the complexity in colatitude, and M is in longitude, and the index for M always runs from 0 up to a maximum value of N. So for example, if you're looking at the dipole term, n equal to 1, m will go between 0 and 1. If you go to the quadrupole, it goes 0, 1, 2.
That's
Right.
how you define, I mean, the way you define 6 and not.
Yeah. So this is going to be the key question here. So this n, you have to choose it in advance, and that's a choice. That's like, where do you truncate a Fourier series, right? You have to have enough functions to capture the signal that you think is there in the data. But if you put too many and you don't have enough data, it becomes unstable. Right.
So we can, for example, just change that to 1 just to do that. And so we just have just modeling a dipole there and push to higher resolution basically by increasing that. But if you go too far, you'll run into problems, yeah. There's a couple of questions there you can answer. The shape of the design matrix, that's the G, and the amplitude of the dipole component there. And if you follow that link to the IGRF, you can see how the model we've just created very naively here, how it compares to the IGRF, which has a lot of effort going into it.
Is it possible to show the source code for design Gauss? I never like using functions just without looking at the code that's underneath. Because that's where all the magic happens. But it's in fact not magic. Yeah. So I can maybe talk through that. So in this function, you can find, all the
This is
details. But if you scroll on down here, so there's a lot of kind of checking of things. But so in here, it's computing this p and m's. So this is there's a function called Legendre polynomial where you have the maximum degree and the value of theta. Yes, and then if you scroll on down, so here, this is, so what they're calling A is what we call G. But you see, it involves, this is cos m phi, that's cos m lambda, that's a longitude dependent, sine m lambda. So before it's compute the polynomial part, this is the, and then here, this Rn, I think that's defined further above somewhere, actually, if you can find where Rn is defined. Yeah, it's here. So if it's internal, Rn is radius to the power of n plus 2. And if it's external, it's radius to the power of n minus 1, it's minus n plus 2. So this is the same radial dependence as you had in the spherical harmonic expansion. So it just codes the different bits, the radial dependence, there's a standard function for getting these Legendre polynomials or associated Legendre functions. And then basically down below it just is combining these things, putting them together to get the design matrix for a radial component, a theta component, or a phi component. Yeah. So you'll see how there's no magic. It's just coding that formula.
You're really good, Chris. It's totally magic.
Some people think like these, how do you do it? You use Chaos Magpie. No, you use the spherical harmonic expansion.
So this code, everybody has access to it?
Yeah.
Like there was just one guy that wrote it and he can use it, or you can correct it too?
These codes, they have been developed over decades.
Okay.
So originally it was written in Fortran, and then it was ported to MATLAB, and then Clemens recently ported it to Python. But these have been tested between different groups, and as part of the IGRF, that's also a kind of test that your code is working okay. And this particular chaos magpie, so I'll talk about this thing called the chaos model. That's something we make in the Technical University in Denmark. But so this particular code was written originally by Niels Olsen in MATLAB, and then he's making that freely available. And then because most people are using Python now, Clemens has put it into Python, so that's freely available with very permissive license, so anyone can take it and do what they want with it. Yeah.
Yeah, a lot of the different modeling groups will have their own code that they've built up over years, and some of them might be using this, but in general they probably have some other code. But yeah, and it's just something that was developed as part of the background behind supporting the chaos model.
So you're suggesting people try to increase Nmax from 6 to something bigger to see what happens?
Yeah, you can.
Because you would think naively, okay, if I just increase Nmax, I should get a better model, right? I have more model parameters. So you can try and repeat increasing this. So it makes the G matrix will have more columns because you have more model coefficients.
6 is almost right.
Yeah.
A little bit more, but
Yeah.
The next steps we start to look at how well the model is performing, and then once you've looked at that, you can go back and increase the truncation level and repeat all that.
But I think the basic answer is that if you go much above 6, with the ground observatory data, it starts to explode, like Kieran. What did you put it to there, Kieran?
13.
13, yeah. So IGRF, as we'll talk about in a moment, it is normally going up to spherical harmonic degree 13. And the reason for 13 is, you remember I showed you that spectrum before that had a very steep bit and then a flat bit? That transition happens at 13. So normally if you want to capture the core field, you need to go at least to 13. So there's some physical reason for cutting there. But the ground observatory alone, you can't go up to 13. You need, and that's because there are gaps. Yeah. But it's still very interesting to see. It's certainly a lot more than just a simple dipole. And that's one of the things I hope you all take away if you're not deep in this topic, is that the present magnetic field is much more than just a simple dipole. To fit the data well, you need to go and include the non-dipole parts of the field. If you're wanting to look at Earth's surface, or if you're going down towards the core and the dynamo, you definitely need these non-dipole parts.
13 degrees.
No.
So if you wanted to go to 13, one way you could try would be this thing that I mentioned briefly called regularization, where if you then try to include an extra term that says build me a model to degree 13, but also has, let's say, the smallest value of the squared radial field on some surface, like the core surface or something.
I think there was a model where they were using a certain energy at the limit of between the before the mantle or the limit of the boundary for the regularization?
Yes, that's right. So that's a way where you can try to go to higher degree, but then you have to do more than just this least squares inversion.
Yeah, and you also
Yeah.
include some limitations that you're not very sure about. So
Yeah, you're somehow biasing the model by doing that. You're biasing it in a way you know, which is you bias it for the radial field at that surface to be small, right? But so, for example, if you're working like Monica, who's the expert on this, with building these type of models from paleomagnetic data, then you also have imperfect distribution of the data, and then you need to do this type of regularization. It's very important. Yeah. So yeah, it's a very crude way to control the complexity of the model, the truncation degree. Yeah, but it can show you at least where your model is very nicely behaved up to, and beyond that, you need some extra information. Yeah.
So this is the part here where you can try a different n max. So you know, if you try going higher, it starts to look quite wrong. If you go up to 13, it's completely wrong, right?
But that's interesting where it's wrong. It's
Yeah.
wrong in the Pacific where you don't have data.
You go scroll back up to the map where the locations are actually just to show.
Yeah, sure. So there's just a huge gap here,
So
right?
that's where you need the Pitcairn data.
Yeah.
I'll jump ahead a bit. So what you can do is you can look at to assess your model, you can look at the residuals. This is how far how much each observatory measurement is deviating from your model. And so you see here there's a very wide range. And then plotting the residuals there, you can see they're quite far off. So our model is not well capturing the actual field at each location. Although, you know, overall it looks sort of reasonable. When you go and look at a particular locations, it's very different. Yeah.
Yeah, so it's very important not just to look at the model output. Your model can look okay, but you should check you fit the data right accurately. So
what do you think is responsible for the discrepancies?
Well, here the discrepancy is because you have, in a sense, too many model coefficients for the number of data you have. So it's badly determined, and that means that some of your model coefficients have bad values after you do the inversion. So it's essentially, if you look at this least squares solution, so this is this least squares solution, that thing in there, that matrix that you have to invert, so this thing GTG, so this depends on this G is this design matrix. That has built into it all the positions of your data, right? And that thing, you can look at its stability by, you can look at what's called the condition number of that matrix. So that's the ratio of the largest and smallest eigenvalue of that matrix. And if that has any singular values that are close to 0, when you try to invert it, it blows up, right? And when you have, if you go to too high spherical harmonic degree with a bad data distribution, that matrix becomes close to singular, right? So that it's a kind of numerical instability in that matrix that comes about because of your data distribution if you go too high in spherical harmonic degree.
So like in the case of IGRF now,
Yeah.
have observation data.
So in IGRF, which we'll talk about in a moment, we use, so here that's only the ground data. So for IGRF, also satellite data would be used. So there's no issue. This kind of problem does not occur for IGRF. This is why it's good to have satellite data, partly. Yeah.
So I'll demonstrate the next notebook now, which is this modeling with swarm data. So we'll see a different kind of regime where we have lots of data globally distributed. So if you open that, it proceeds similarly. We fetch some data, but this is using the same routine that we were looking at before the break earlier on, doing that data selection. So you see here we have now 7,500 data points, and that's the vector that we're going to use. So this is essentially doing the same thing that we did using our ground observatories to make a model. The one difference is here is I've just limited the inversion to only be using the radial components. So we're going to make a model using just the radial component, not the full vector. So here, it just immediately went to degree 13, and it's behaving reasonably.
Yeah, maybe we don't have time to do it.
Yeah, I think we don't have time to go into the exercises exactly. But again, you can look at the residuals, but it's more complicated because we've got a lot of data points.
The main thing to notice, so this is the difference between the model prediction and the data. And so the scale here is plus minus 40 nanotesla. So it means you're fitting this 50,000 nanotesla signal to within, in this case, 40 nanotesla. But in fact, most of the data at mid and low latitude is being fit to 10 nanotesla or less. And the big values are nearly all in the polar region. And that's because in the polar region you have these polar current systems that you're not modeling. Remember, we assumed J was 0, and that's actually not really true at high latitudes because of the auroral currents. So that means it's not in your model, and that's why it ends in the residuals at high latitudes. It's crashed.
Yeah. It'll come back in a minute.
Is it too many people or?
I don't know. Yeah. I think we didn't have these problems last year. Yeah. But it should just come back in a minute. Okay, so anyway, here we were looking at the vertical component, the residuals for that. And if you look at the eastward component, you can see they're quite a lot stronger, and you'll see the same in the northward component probably as well. And this is just to do with, I mean, what you're capturing here, it really is these polar currents, and it's to do with the geometry of the currents that are coming in, which vector component magnetic field is most responsive. So what you can see from this is, yeah, if you look, the vertical component is less. If you're talking about the core field, trying to model core field, this vertical component is less contaminated than this eastward component. And that is actually part of the reason why I chose to do the inversion just using the vertical components. So if you go back through it again and extend the design matrix there to use the, so that's, yeah. If you modify these lines to extend to use the other components as well, you might actually see a degradation in the model, even though you're putting three times more data in, because those components are more contaminated. It can degrade the model. So you might want to do something different for each component. It's also interesting to look at instead of plotting against geographic coordinates there, you should plot against local time coordinates. So there's local time, and so that's why all of our data is around here and here, because that's the night side data that we put into the model. I mean, if you put more data into here, you would actually see real structure related to the auroral currents. Yeah, so this is looking at the residuals binned across latitude. So with each of the components, this green line is the vertical component, and the orange and blue are the horizontal components. And so there you can see it's really why the vertical component is less noisy there.
IGRF, and we have in the audience Kieran, who is the chief of the IGRF this last time round, so I will be directing all questions on this to Kieran. So I'll talk quickly about this, and then after that I'd like to go on and finish off by talking about some more state-of-the-art models which are more complex, but I'd like to show you what's possible. So the last part will be more the kind of research talks that will be happening next week. That'll be a quick tour. But first of all, what is this thing, the IGRF? So IGRF, so this stands for International Geomagnetic Reference Field. So the idea really behind this, it's a kind of standard geomagnetic field model. So there's a need out there in the world. If you need to know what the Earth's magnetic field is, where should you find that out, right? Which you could have all different groups building models and so on, but which one is right? Of course, none of them are completely right, but we as a community, it was decided there was a need to kind of communicate the state of the art of the knowledge of this in a way that was usable to the wider community. So that's where this IGRF came about. So it's a model that's produced by Division 5 Working Group VMod here in IAGA. And it's freely distributed, okay? So it's built as part of the standard work in a number of institutes, and then it's put out there without any cost for anyone who wishes to use it. So the IGRF is I would say, very widely used for many scientific applications. So for some studies of core field, for example, paleomagnetists might use it. For crustal field studies, you often want to remove a model of the core field before you look at the anomalies. Also in space physics, so as those of you working in space physics will know, the geometry of the currents in the ionosphere and magnetosphere is basically set by the geometry of the internal magnetic field. And if you take the IGRF, that can tell you the geometry of these current systems. So many space physics models will take, if they want to do more than just the crude dipole, they'll take IGRF as an input. And so what it's doing, it's describing the large-scale internal field. So just the internal field and only up to spherical harmonic degree 13. And so that means it's using this expansion that you now have seen several times, right? So what in practice is provided is a list of these Gauss coefficients or spherical harmonic coefficients, G and H, for different degrees and orders. And what happens in IGRF is every 5 years there's a new set of coefficients. So it's updated every 5 years. And then for this set of coefficients every 5 years, if you want to know the field in between these 5 years, in IGRF you find that just by linearly interpolating between them. So the assumption is within 5 years the field changes linearly. Now that's not true totally in practice. The field can have sharp changes, but it's often enough for many applications. So what happens is when a new generation, as they call it, of IGRF is produced at the latest epoch, so this year it was for 2025, a new set of coefficients were produced. Now those are provisional. So that means they're the best we can do at that time, given the ground observatory data we have and the satellite data we have. But we know we might update that in the future. So they're provisional. And also an estimate is given for the linear rate of change. We call that the secular variation, but that's only up to spherical harmonic degree 8. And using this secular variation, you can extrapolate, and it's not advised to do that for more than 5 years, but in 5 years anyway, an update will come, right? Yes. So the latest update was led by Kieran here and by my colleague Clemens Kloss at DTU. And so they produced a new provisional IGRF for 2025, secular variation for 25 to 2030, and what's called a definitive model for 2020, because we know there's probably no more new data at this point going to come for that. So the way it worked was that different teams produced their own internal field model, doing the kind of thing that you've been doing in the notebook, but maybe a bit more complicated models. So they all did their own data selection with whatever data they preferred, whatever exact modeling setup they preferred, and then they submitted this. And so I think, if I'm right, Kieran, there was 19 teams from 27 institutions and from many different parts of the globe, from Asia, from Europe, US, even Russia was involved, Africa. So quite, as the title says, international, right? And then these were then assessed by a task force, and this is now, as a new, I think, very nice innovation, all been done completely transparently, so you can go to GitHub and find out the analyses that were done to evaluate the different models that were submitted. And then the task force voted on a way of combining all these candidate models. And so the way that was done was for this model in 2025 and for the secular variation, there was a kind of a weighted mean was taken in physical space. So they evaluated the model in physical space, and then they took all the model predictions on a grid and then averaged them with some what's called Huber weights, which takes account of long-tailed distribution. So it's some kind of robust statistics. And then for the DGRF, it was simply a median of the coefficients. So that was a bit simpler, yeah. So, and then these kind of averaged models were then released as the IGRF products in November last year. And you can find this on the NOAA IGRF webpage. And I think also very nice now, the coefficients were also archived on a Zendo repository. And there is a special issue of Earth, Planets, and Space that Kieran is editing together with Clements that is in production. And this special issue basically, many of the people submitting candidate models will describe how they built their model, and then there'll be a paper describing the evaluation and how the model was combined, and so then everything is well documented. Yes. Anything to add, Kieran? Is that okay?
Just Ashley helped as well.
Yes, a lot actually with the GitHub. Thank you for pointing that out. So with this evaluations, Ashley was doing very nice work on that. Thanks, Ashley, for that. Okay, so here's the kind of results. So this is a map showing the declination. So blue is when the local magnetic vector is to the west of the geographic north. Red is where it's to the east. So if it's white here, like it is close to Portugal today, it means that the magnetic direction is more or less north. But if you're up in Greenland, it's 25 degrees to the west of the geographic north. And if you're in the Southern Ocean, it can easily be 30 degrees east or west. So, and this map, of course, is changing with time. That's why we need to update it. This is the inclination. So you see the dipolar structure here, and there's the clear anomalous behavior in the South Atlantic. And that's very evident again in the field intensity. So here the yellower colors are where the field is strongest. So again, strong field over Siberia, strong field over Canada, very strong field here south of Australia, and then weak in the South Atlantic. Okay, so if it was just a pure dipole, it would just get stronger as you went towards the North or South Pole. So it's certainly much more than that. So that's this, and this is a map of the horizontal intensity, which is if you don't include the vertical part. And the last picture here is about pole movements. So this is in the northern hemisphere on the left and the southern hemisphere on the right. So there are two, people get very confused about magnetic poles. Let's try and be clear about this. Right. There's something called the geomagnetic, I would call it dipole pole. That's when you take just the first three terms in the spherical harmonic expansion, the dipole part, n is equal to 1. And that has moved according to the blue dots between 1900 and 2030. So it hasn't moved much. It's moved a little bit up in Greenland and in Antarctica. The other magnetic pole that people talk about is where the field is completely vertical. So that's what's called here the magnetic dip pole. So it's where the dip is purely vertical. And that one depends also on the non-dipole parts of the field. And that one has changed, especially in the northern hemisphere. It's moved very dramatically between 1980 and 2020. It went very fast from at about 40 kilometers per year from Canada over towards Siberia. And it does something completely different in the southern hemisphere. That's because the non-dipole field is different in the northern and southern hemisphere. Okay, but so the IGRF provides information on all these things.
So to point out unusual features, next year the two magnetic dip poles will have the same longitude, which I don't think has ever happened before.
Okay.
Certainly not on the record.
Okay, so then they won't be antipodal, they'll actually be in the same hemisphere. Yeah. Yeah, but that's why you shouldn't think that the Earth's magnetic field is a pure dipole. Yeah. Okay, good. And we've already had the practical, so that's fine. Okay, are there any questions about IGRF? So there'll be a whole session on Monday where many of the people submitting the candidate models present what they'll do, and Kieran will be chairing that.
Yeah, well, you can skip the first talk because Chris is basically giving my talk. That's all I can say.
Okay, good. Right, so now I want a very quick tour of some more advanced models of the Earth's magnetic field. So I actually had already mentioned this thing called the chaos model of the near-Earth geomagnetic field. So chaos is an acronym, actually. So it stands for, originally it was some acronym made from the names of the satellites, CHAMP, Ørsted, SAC-C, and then, okay, SWARM was also S. So this chaos model was basically a model largely built on satellite data, and it's a model of the near-Earth geomagnetic field, quiet time near-Earth geomagnetic field, that's designed to have high spatial and temporal resolution. So this is a model that was basically pioneered by my colleague Niels Olsen in the Technical University of Denmark, and essentially over the last 2 decades, this model has been developed by myself and now by Clemens Kloss as well. So this is an observation-based potential field model relying on satellite data and also ground observatory data. So it provides not just this internal field to degree 13 in static coefficients every 5 years like IGRF, but it's a fully time-dependent core field. So we expand these spherical harmonic coefficients also in time. And for the static internal field, we go up to a much higher spherical harmonic degree to also catch the sum of the crustal field. It also has an external field model, which is mostly designed for quiet time magnetospheric fields. And the latest version now also includes a climatological ionospheric field model. This thing, it's fairly widely used, I think, for people who are, especially if you're interested in fast dynamics of the core field. So there's a web page here where you can get that model, and this thing, Chaos Magpie, that you were using a function from, that's a Python package designed to use that model. Yeah. So I'll briefly say, so this Chaos 8, it was what we used to generate our candidate for IGRF. So that's a kind of, we call it a parent model, right? So this was built, this is a plot showing the data. So these are all the satellites that we've used. Most recently, it's been SWARM, and also red is the Macau satellite data. And this was the amount of ground observatory data that we've used. So these are the locations of the ground observatories we've used. And so here it's number of data, but it's vector data. So divide that by 3 to find the number of stations per, I think this is per 3-month interval. So because of this delay in the observatories reporting definitive or quasi-definitive data, this is decreasing towards the most recent epoch. But there's still some hundreds of data for the most recent times. Very quickly, how is this model parameterized? So the internal field looks essentially like what we've seen before, but now these Gauss coefficients are time dependent. So here I've done something a little different with this is a more compact way of writing this expansion. Here I allow m to go to -n. The minuses are taking into account the sign dependencies in longitude, but it's similar to what we had before. Then these internal Gauss coefficients are expanded in a basis of B-splines. These are local polynomial functions. And then for the magnetospheric field, we use an external field that we use not geographic coordinates, but solar magnetic and these GSM. This is another space physics coordinate system. So these describe essentially for the ring current and far magnetosphere, so magnetotail and magnetopause processes. So yeah, it's a bit more than just expanding it as an external field is what we showed in the simple solution earlier, but it's a spherical harmonic model again. And so we have an internal field, time-dependent, external field, and then a climatological model of the ionosphere. And we also solve for calibration parameters for platform magnetometers. We're using these platform magnetometers here. And we also solve, we use the satellite data not in the neck frame, northeast center frame directly, but in the instrument frame on the satellite. And we solve for some alignment angles for each satellite that help us do things a little bit more accurately. Okay, I won't go into the details here, but it's again, there's some cost function that we're minimizing, and it's the difference between the data and the model prediction with some weights and some regularization, all right? And this is a nonlinear optimization problem. So we solve, in our case, we had 41,000 model parameters that we solved for from about 11 million data. And we were fitting the satellite data for swarm, for example, for the radial field, we were fitting it to about 1.4 nanotesla. Okay, so that's a bit more than the 30 nanotesla we were talking about earlier. And the fit to the Chinese MSS satellite is slightly higher, but very similar. So my colleague Clements will talk about that in more detail on Monday if anyone is interested. So the results, very briefly, so this is the radial field at the Earth's surface from this chaos model. And what we're more interested in this model, this is the field at the core surface, like I showed you earlier with the movie going down. Okay, so and here we have this time-dependent core surface field that we have its time dependence over 25 years. So this model starts in 1999 when we had this Ørsted satellite being launched. So we can watch the time evolution of this over 25 years to high resolution. The first time derivative of the field, so at the Earth's surface, the field is changing most actually at the moment over the Americas in the radial field component. When you downward continue to the core surface, the pattern of the field changes is rather small scale, but there's a very distinctive pattern in high northern latitudes in the polar region that you don't see in the southern hemisphere. I'll come back to that in a minute. And you can also, with this model, look even at higher time derivatives. This is the acceleration. Okay, so now what can we do with this kind of model? So I want to come back a little bit very briefly to how we learn about what's happening in the Earth's core, right? So a few of you have asked me, what happens, where's this South Atlantic anomaly coming from and so on. So to do that, we have to go in the core, right? That's where the action's happening. So that we can do using something called the magnetic induction equation. And this relates motion of the conductor, which is given here by the vector u. And so essentially what happens is that the conductor in the core pulls the magnetic field around with it. So when we look at the change of the magnetic field, the secular variation, and if we know what the magnetic field itself is, we can try to invert for the flow, for the motion of the liquid metal that's causing the field change. So this is one of these inverse problems where you have to try to get at the flow. So what's shown below here is a map of the flow at the top of the outer core that we obtained by inverting the results from this chaos model for the field rate of change. And this was shown here in 2020. So there's a few things to notice here. The biggest pattern is there's this large circulation that you see in both hemispheres. So this is what we call this is a very big anticyclone. So this is going westward in this hemisphere, and then things are moving poleward and then wrapping back round. So it's going in the opposite sense to the Earth's rotation, so it's an anticyclone. And this is what produces, some of you might know that the pattern of Earth's magnetic field is largely drifting westward. Right? If I showed you this map of the declination, and I showed you it 50 years ago and today, you'd see the whole thing has moved west. And essentially this big anticyclone is pulling things in that direction. So this is a difficult inverse problem, and we have to use some additional constraints that we get from numerical simulations of this dynamo process in the core. So I'm not going to go into all the details of this. There's at least one person in the room who knows about this. If you want to study the physics of the Earth's core, you essentially need to solve three equations in parallel. One is the conservation of momentum. That's the Navier-Stokes equation for fluid flow. It contains acceleration, inertia, Coriolis forces, buoyancy from the convection, Lorentz forces because you have a magnetic field that's stopping the fluid from doing what it wants, and viscosity. So that's telling you about the conservation of momentum of the fluid. Then you have an equation for the time evolution of the magnetic field that basically comes from the conductor pulling the magnetic field around, and from the fact that you have finite conductivity, so things are diffusing. And you have to solve for the evolution of temperature, transport of heat. So you have a temperature advection diffusion equation to solve. So we know these equations, and we know the boundary conditions more or less, right? We have some ideas about that. So that becomes a very big numerical problem. You have to discretize it and then solve it on very large computers. But that is today possible to do, especially if you make some approximations. And so what I'm showing here on the top left, this is a map of the flow in the outer core that we got from the observations. Blue here is westward flow, red is eastward. What's shown in the bottom is one of these numerical simulations from Julien Aubert. And you can see in the simulations, we're able to reproduce this so-called gyre structure. So this is the inner core. This is the core mantle boundary. We're looking down. Imagine you're sitting in the North Pole looking down into the core, right? This map view here shows you. And this ribbon is following, it's a kind of tracer of the flow. So you're having convection coming up from the inner core, and then this big gyre. And that's what we see in the observations, and with the models we can reproduce that. So this is a kind of cartoon of this eccentric gyre. High northern latitudes, we've seen between 2000 and 2020, if we look at the chaos model at high latitudes, I said to you there was a special pattern happening in the secular variation in the northern polar region. So that pattern can be explained if there has been an acceleration of the flow in this high northern latitude, so basically underneath the Bering Strait. So we think that there's a kind of jet happening in this high latitude region in the northern hemisphere. And I won't go into it now in too much detail, but if we look at the time variations in this flow, we see evidence for waves happening, especially at low latitudes. So this is the flow at the core surface in 2015 and 2019. And you can see that this pattern has changed sign. So this is an oscillation, right? And we see these things also in the numerical simulations. So in order to use the observations to then come up with a better explanation for what we see, these numerical simulations are really a helpful tool. So really the frontier of understanding is coming on the one side from the observations, but then to interpret them, we need the physics. And today that means we need numerical simulations. And then by the combination of these two things, it's really helping us to make progress in understanding where these changes in the magnetic field are coming from. Okay, so that was a bit about state of the art in the core field. Now I'd like to talk about the small scale magnetic field, the lithospheric field. So here we're talking about what we call the anomaly field. So there what we do is we take the full observed field, we take off something like IGRF, the main field, and we correct as best we can for all the external current systems. And then what we've got left, it's mostly produced by the magnetization close to the Earth's surface, magnetized rocks from the geology. So this originates in remnant and induced magnetization of rocks, dominated by ferromagnetic minerals. This thing, to a first approximation, it's static, although it can change very slowly because the core field's changing, and then this changes the induced magnetization of the rocks very slowly. What's shown at the bottom is a forward model based on geology of the magnetization, the total vertically integrated magnetization of the Earth's surface. So if you want to study this lithospheric field, it's all about small wavelengths, and we can't get that small wavelength part from the satellites. They're too high up. So this is built on ground data largely. So there's something that, again, is an IAGA product, which is called the World Digital Magnetic Anomaly Map. And what's shown in this plot, which is taken from their webpage, is different data sources that are contributing to this World Digital Magnetic Anomaly Map. So the colors are different regional surveys that were then combined. And you can see in the oceans, there's a lot of tracks. That's because the knowledge in the oceans is coming largely from marine surveys in the oceans. So what was done in this World Digital Magnetic Anomaly Map by again, an IAGA task force, was that they combined all these local grids, and where they didn't have any direct measurements, they filled it with satellite data, which is too smooth, too long wavelength, but it's all that they had. And then this was all combined into this World Digital Magnetic Anomaly Map. And so the state of the art for this lithospheric field part is shown by this thing which is called XDF-LI. So this is, again, a lithospheric field model this is based on swarm and champ data that has been combined with these World Digital Magnetic Anomaly grids using quiet time data and doing corrections for the core field and the magnetospheric field. And then there's been 1,000 regional models built. So this is using the spherical cap method that you mentioned. So there's 1,000 regional models are built using the spherical cap method, and then these are combined into one big spherical harmonic model that goes out to degree 1600, right? So you were messing around with degree 6. There's a lot of data here, right? And so you can see in this map, as much as we know right now of the detailed structure in space of Earth's magnetic field. And this is the spherical harmonic power spectrum. And this is on a logarithmic scale in this case. So when you go to very high degree, the spectrum starts to turn over. We were previously looking at it here when it was pretty flat. If you go out to degree 500, it starts to decrease again. Yep, so this model is developed by Erwan Thibault, and it's available for those interested in geological interpretations. So the final target regarding internal fields that I'm going to mention is what's called ocean-induced magnetic fields. So this is a much smaller signal. This is really at the limit of what we can do today with satellite data. So what's going on here is, you know the ocean, that's salty water. That's in fact a conductor, right? And that conductor is moving through the main Earth's magnetic field coming from the core. And if you have a moving conductor moving through a magnetic field, Faraday told us you should induce voltages. And if there's a closed conducting path, you're going to get electrical currents flowing. And these electrical currents, they have a magnetic field associated with them, which is very small, but that's measurable, okay? So this ocean-induced magnetic field, to get it, you need to integrate the induced electrical current density over the oceans and the surrounding conducting Earth. And this current density, it comes from the velocity in the oceans moving across the magnetic field and then any additional electric fields that are around. And again, there's one of these magnetic induction equations that tells you how this ocean-induced magnetic field changes with time, depending on the velocity in the oceans. And sigma here involves the conductivity of the oceans. So if you can measure this ocean-induced magnetic field, you get information on the flow in the oceans and the conductivity of the oceans. Now, the conductivity of the oceans, that depends on the temperature of the oceans, and it depends on the salinity of the oceans. So you're getting, in principle, information about the velocity, the temperature, and the salinity of the oceans, and you're integrating that over the entire volume of the oceans, not just looking at the surface of the oceans, which is normally what many remote sensing of the oceans is doing. Okay, so we've been interested to see if we can find this magnetic signature of the oceans. And so Alexander Greiver, who you'll hear from tomorrow, I've done recently some work in collaboration with Alexander where we've tried to pick out the signal from the ocean due to the tides. So you know that the oceans have tides. There's actually several different types of tides in the ocean based on the gravitational attraction of the moon and the sun and different ellipticities involved. So what's nice about this is we know very well the exact periodicity of these tides. So that means that we can look in the magnetic data for a signal that has that exact periodicity. That really helps with data processing. So using CHAMP and SWARM data, again, dark, nighttime selection, quiet time selection. I can see there's a few typos here. This was late. We can invert for spherical harmonic models. So what's shown down here below is on the left column, it's the observed ocean tidal signal. This is for the M2 tide. So this is the semi-diurnal lunar tide. And this is what the induced magnetic field, due to this that we pull out from the data is. It's about plus minus 2 nanotesla. The top row here is from the observations. This is the real and imaginary part of this periodic signal. And the bottom is what you get from simulation, where you take what people think the motion of the ocean tide is and some model of the conductivity of the ocean. And you solve the forward problem, and you see they agree, not perfectly, but very well. So this is strong evidence that we can pull out this ocean tidal signal. That's for the M2 tide, that's the biggest one. This is another tide called Q1, so this is a diurnal elliptical tide. This has an amplitude of 0.1 nanotesla. That's tiny, right? Remember, 50,000 nanotesla to 0.1, that's 10 to the 5. So here, the agreement between the observations and the simulations is not as good, but we think we can get some of the features starting to for this, even this very smaller tidal signal. So the tides, they're interesting, but they're already rather well known. What I'm more interested in is the signal due to the ocean circulation in general. So this is a picture from, again, one of these forward calculations. So given some ocean flow, temperature, and salinity, and acting on the IGRF with that, this is the induced magnetic field from the oceans. So this is plus minus 1 nanotesla. This is now not the tidal part. This is due to this general circulation of the ocean, the thermohaline circulation. Okay, and this is strongest in the southern oceans. There's a very big current there, the Antarctic circumpolar current, that produces that thing. What's even more interesting is if you filter that, for example, to look at seasonal or annual variations, you see a lot more structure. You see things in the Pacific Ocean that are related to the annual cycle in the Pacific Ocean. This is affected by El Nino. You see very strong signals. The strongest signals are in fact in the Indian Ocean. So what I've recently been doing is building field models, time-dependent internal field models up to degree 30. So not degree 13 or degree 20, out to degree 30 with a 2-month knot spacing, using swarm gradient data and focusing on solar minimum years to try to get away from external effects, and then applying some filtering. So what's shown on the left is what we get out for this annual signal in 2020. So this is the radial component in the Indian Ocean, and that's the left column in January and in July, and this is in the right column what you get from simulations. So again, they're not agreeing perfectly, but at least I'm encouraged that there is some real signal here that if we work a bit harder, we can do better with. So the reason I'm interested here, the Indian Ocean, you have something very interesting happening due to the monsoon. There's a current flowing in the Indian Ocean that changes its direction associated with the monsoon. And in principle, you can monitor things related to that if you can pull this signal out properly. But it's a small signal. It's about 0.1 nanotesla, so not easy. Yeah. Okay, so that was my quick tour of the state of the art. I'd like to finish by pointing out there's actually plenty of things we don't know still here. So the limitations that we have that stop us from learning more, I think regarding the core field, the biggest limitation is, especially from satellite data, we only have 25 years. And the core field is changing slowly, right? So the time scales for which we have high resolution records are short compared to the physical time scales of interest. That's a challenge. So that's an argument that we need to continue our observations for much longer if we really want to learn more about these systems. Regarding the lithospheric field, the biggest challenge there, I think, is that if you're going to the very small length scales, again, then the satellite data can't help you, and then the data is very patchy. So there's some work needed there to try to improve areas where the regional grids are not complete. Regarding if we go to faster changes from the ionosphere and the magnetosphere, if we look at things in timescales of minutes, we don't really have global coverage. The best information we have there, global coverage-wise, is from the ground observatories. Right? They're there. Every minute, it's there. The satellites at any given minute are in a few places. Right? So for these signals, we really don't have the global picture right now. And a related point to that is with the present distribution of ground and space observations and the modeling techniques we've got, you can only fully separate internal and external and magnetosphere and ionospheric sources if you have good global coverage. And we don't have it. Maybe we have it on very large length scale, but we don't have it to the kind of length scales that are interesting for ionospheric studies, for example, globally. So this, again, so we need observations over a longer time, and we need more observations at any given time, right? That's a fundamentally the observations are what limits us here. Yeah, so to sum up, I think today in 2025, we're actually, I think, very fortunate to have a very high quality ground observatory network, and we've got these multiple satellites, Swarm, McCowSat, NanoMagSat on the way. So I think it's a very exciting time to study Earth's magnetic field. We certainly have a lot more data than when I started looking at this 20 years ago. And there's plans afoot for additional observatories in strategic places and for further magnetic survey satellites. But I would like to strongly argue that long-term observations, so maintaining high standards and replacing existing observing systems, making sure these ground observatories that have been so valuable are maintained is really crucial. If that drops off, we're going to lose the chances that we have of learning more. We also need new field modeling techniques to better utilize these improving coverages that we have from ground and space. And there are, I think, new possibilities to study these very small signals, for example, from the oceans. So there's lots still to learn, so I hope some of you will see that in the upcoming years and be involved in it maybe. So I finish there from my side. Thank you.
So Chris, this was really amazing. Thanks
Yeah.
really a lot, and also to Ashley. I think everyone is really grateful from you, and now they know your faces.
Yeah.
And next week you will be also ready.
Yes. Any questions that come up, you're welcome to come and have a chat next week. I'll be around. Yeah.
This is really great.
And I'll be here tomorrow as well, at least for part of the day, because I'm interested to hear Alexander tomorrow. Yeah.